Yes, yes. Just towards the joining.
Is Santosh joined?
Okay. We'll wait for Santosh sir also.
Okay.
Yeah. By the time Santosh sir will join the meeting, Dr. Neeraj sir
Yeah.
is there.
Good morning, Mr. Omkar.
Yeah. Good morning, sir.
At present, you are in Pune.
Right now, I'm working from my native.
Okay.
I'm at Kolhapur actually.
Okay. But your all the activity will be offline only, no? Physically, you have to go to the
Yeah,
industry.
no, it's like all that is offline. We have started working from the office, but I am on vacation. So currently I'm at
For
my
the
native.
festivals.
Yeah, for the Ganpati festival, yes.
Great.
Kamlesh sir.
Yes, sir.
It's 9:32.
Hello.
Yeah, so it's 9:32.
Yes, we'll, I guess, by Santosh sir is also join the meeting. And as the new students join, we'll start, sir.
Yeah, I request all the class teachers to send a reminder message in the students group.
Okay, okay, sir.
Yes, yes, sir.
Kamlesh sir. Kamlesh sir. Shoaib.
Yes, sir.
Mr. Shoaib.
Yes, sir.
Coach sir is having some issues. Just call him and just find out.
Okay, sir. Okay, sir. I'll just call him back.
Yeah, coach sir join, I think. Good morning, sir.
Good morning, sir.
Okay, Santosh sir, am I audible?
Yes, sir, you are audible.
Santosh sir?
Good morning, Santosh.
Good morning.
Yes, actually we were
Yeah, sorry. Actually, I have joined, but there was some error. Am I audible?
Yes, yes. Good morning, Mr. Santosh.
Uh, Good morning, sir.
How are you?
I'm good, sir.
So, Santosh,
Yes.
can you recognize my voice?
Yes.
Just a second. I think no image is coming up.
Coach sir is there.
Santosh, it's coach sir.
Oh, oh, sir. Sorry.
So, how are you?
I'm good, sir. I'm good.
So, what is going on?
Uh, CFD, nothing else.
Nothing else, only CFD now. Huh?
Yes, yeah, I can just say that this is kind of a different experience. So probably if you give me this kind of chance again and again, this will be an additional thing to me.
It's fine.
I'll be interested.
Now, which company you said you are working currently?
It's Teneco Clean Air India Private Limited.
Mm-hmm. Mainly, what kind of work they do? Domain?
Teneco actually, as a Teneco, it's a US based MNC, and it has mainly three domains. One is clean air. Clean air is to do with you can say exhaust system engineering and manufacturing. Then one is ride and performance, or which is now called as drive. It is related with the shock absorbers. And third one is powertrain. So that powertrain deals with the subcomponent of the powertrain, like piston rings, bearing, valve shaft, like that.
Are you also working towards electrical powertrains and drives?
Okay, probably I am going to like looking for the company which can offer me that kind of work.
No, I think everyone will start in that direction because that will be the future.
Yes, true.
Companies they started.
Actually, our company is also working doing R&D in that direction, but till now we haven't get any RFQ or real time work. So let's hope we'll get something in future.
Because the mainly in that particular domain, because basic philosophy is changing, your input forces are changing.
Yes, sir.
So that will make again another interesting story, because Till now, nobody walked in that particular direction, particularly in electrical drive. Your entire automotive system, power drive is changing. Because of that, powertrain will change. And because of
Yes.
drive and powertrain, even suspension and even vehicle comfort, everything will change. The loads
Yes.
coming on the vehicle also will change.
True, true.
I think now people may not be focusing on all that aspect because now everybody is in a hurry to launch their electrical vehicle.
True, that is true. Actually, this is like a very initial stage for EV in India.
And even I heard one of my colleague who is working actually has his own company and then working many years now in electrical vehicle domain. There is again next disruption is already existing because your battery systems will change. So now
Yes, there is already dry battery and weight battery. There is already that kind of discussion going on, which is better
now,
one.
New materials can have a larger energy density, compact size, charging time will be very less. So even lithium ion also will disappear, and all those companies, if they are not changing, they may have to close down.
Yes.
This is the 10 years period. Next 10 years, lot of changes will come.
Yeah, it will take maturity till that time.
Now even business model also is changing because everything is changing surrounding. So business model also will change. Your vendors will change. Vendors approach will change. Many things.
Yeah, I expect that till then IC engine will also have something which increases longevity because there is already many $1 billion has been invested in synthetic fuel, and at least the initial level result seems good, but the main issue right now is the cost. So until and unless it becomes cost effective, it will not really like capture the market. But it might happen in next 4, 5, 6 years, and IC engine could get rejuvenation again.
And see, when IC engine was invented, that time it was a breakthrough in many aspects.
Yeah.
Things will come and go many way. So, but the technological disruptions are taking place at very rapid pace.
Yes.
I think everybody should accept that and start aligning because we don't know what is going to happen. And particularly this digital technology is creating an issue.
Yes, yes.
And you are upgraded like anything on technology front, and then if you are not keeping pace with other developments, some other player will come and then take a market. That worry is there for all the players.
I think engineers has to be very energetic and adaptable in coming years.
It is mainly the question of adaptability. One should not be very emotional about one thing. You should be easily adapting to the changing requirements. That will be the future.
True. But I think being a mechanical engineer of 2000 start era, we always used to have some special love towards IC engine.
Problem is not with that. I think mechanical will lose this particular distinction of what manufacturing, design and thermal. All are now getting integrated. It's not only mechanical. Other domains are also coming into the system. So you don't have any product wherein your IT or electronics is not integrated as such.
Right.
So AI is already existing in mechanical only, but IT people are claiming, oh, now new AI. But that is many years already it is in place, no?
Yes, true. Even I think the guy who is nowadays become huge sensation, Elon Musk, is actually an IT guy.
But he's doing
actually an IT guy. Yeah.
No, finally the product realization only happens either through electrical or mechanical. Even
that is actually core thing.
Electrical has limitation because it is only drive. Final product won't come through electrical.
True.
So, but I think many things are changing, but mechanical also supposed to adapt. Because if you are very rigid in some segmental aspect, then it becomes a problem. Because mechanical from beginning, it is adapting to the changing requirements. Even your CAD/CAM and all, it is digital, no, computer based.
Yes.
Adapted,
Yes.
integrated. Now, similarly, electrical and electronics also to be integrated and IT also to be integrated. Because IoT and AI, major applications only in mechanical domain. Whatever you can say, but that final application will come only in mechanical, no? Because final products are in mechanical form.
Yes.
So, these are the issues. Huh?
Yeah, shall we start?
Start.
Kamlesh sir?
Yes, yes, yes. Shreyansh, please share the screen.
So good morning everyone. My name is Aditi Shinde and I am the Joint Secretary of MESA.
And I am Pratham Kumbar, and it's our pleasure to host this webinar. On behalf of the entire MESA team, we welcome you all to Synergy 2K21.
MESA stands for Mechanical Engineering Students Association. We host a number of events throughout the year, namely Synergy, MESH and Caliber.
These events are possible due to the contribution of brilliant minds and dedication displayed by our MESA committee under the leadership of staff coordinators and our head of department.
As the name suggests, Synergy is the symbiosis between the knowledge and company experience. It is a bridge between academic and professional sector, and today we have eminent speakers from Tenneco Clean Air India Private Limited who are here to share their valuable industry experience with us. Tenneco is one of the world's leading designers, manufacturers, marketers of automotive products for original equipment and aftermarket customers. It is one of the Fortune 500 companies.
Now, let us have the lamp lighting ceremony, which will symbolize the start of Synergy 2K21. With the permission from guest speakers, Principal Sir and HOD Sir, we would like to do the lamp lighting and proceed with the event.
Go ahead.
Yes, please.
Now, I would like to introduce the senior committee members. President Aditya Bhaskar, Secretary Malcolm Dias, Joint Secretary Aditi Shinde, Treasurer Adhiraj Londhe, and PRO Natesh Shetty. We also have a sponsorship committee which has Pratiksha Pawar, Pratham Kumbhar, and Shreya Dupeskar. And last but not the least, the magazine committee which has Omkar Parkar, Ritu Khimasia, Yash Chaudhary, and Shriyans Murari.
Now I call upon the President of MESA, Aditya Bhaskar, to express a few words on behalf of entire MESA Council.
Thank you, Aditi. A very good morning to everyone present here. I, Aditya Bhaskar, the President of MESA, on behalf of the entire MESA Council, would like to greet and welcome you all to Synergy 2K21, an interactive webinar session where students will get the opportunity to interact with the industrial personnel and enhance their knowledge and skills. MESA plays a vital role in the development of students as engineers through various co-curricular activities. MESA aspires to inculcate among its members an awareness and appreciation of the various disciplines. Today, MESA, with its highly dedicated committee under the able guidance of our faculty coordinators and HOD, is committed to achieving all its goals. MESA aims to promote the interests of students in various technical areas pertaining to mechanical engineering. We also aim to focus on the cutting edge technology prevalent in the industry and present it to the students by means of lectures, articles, webinars, workshops, etc., so as to bridge the gap between the theoretical and practical knowledge. We, as a team, also interact with the other technical societies within and outside the institute to promote the exchange of ideas and knowledge. This in turn allows the creation of a platform for interaction between the faculty and the students and a friendly bonding between the seniors and the juniors of the department. Now, coming to the activities of the MESA Council. Every year, MESA conducts numerous events with the motive of delivering quality and maximum contents of knowledge to the students. Every year, MESA organizes Synergy during the odd semesters with a view to bridge the gap between the industry and the institute and provide an opportunity for the students as well as the faculty members to directly interact with them. Due to the COVID pandemic last year, Synergy was conducted in an online platform on 5th of December 2020, where we had speakers from Mahindra and Mahindra Nashik plant. MESA also releases its annual technical magazine, Urja, every year, which consists of articles written by our own students on a particular technical topic. Urja 2019-2020 edition, themed as Industry 4.0, was released during the Synergy event by the hands of our HOD. MESH is organized during the event semester where seminar lecture series is organized and expert speakers from research institutes and academic institutions like DARC, IIT, IIITs, etc. are invited to deliver lectures in their areas of expertise. MESH 2K21 was conducted online, which turned out to be a huge success, and professors from IIT Bombay and IIIT Allahabad were invited to deliver a webinar for our students. The biggest and the most renowned event of the mechanical department, Caliber 2K21, was conducted in collaboration with the Institute of Engineers India, Belapur local chapter on 29th and 30th of April 2021. National level events like the national level project poster competition, national level technical paper presentation competition, along with thrilling events like CADICT, Quizophile, Auto Auction, and Tech Talk were held, and students took part in these events with great enthusiasm. This time, COVID helped us in reaching the colleges nationwide, and students from more than 40 colleges all over the country participated in the events and contributed to the success of Caliber 2K21. The MESA team, with the substantial guidance and support of the management, Principal Sir, HOD Sir, and the department, has made it through every tough situation. Their matchless efforts will definitely prove valuable in bringing MESA and the mechanical department to the brighter reality in the coming academic years in FCRIT. I thank all the dignitaries, faculty members, and my fellow students for their support and participation in all the events organized by MESA and look forward for more enthusiastic participation from your side as we come up with new and exciting events for you all in the near future. Thank you.
Thank you, Aditya. Now, we have with us the speakers from Tenneco Clean Air India Private Limited, Mr. Santosh Satre, Senior CFD Engineer, and Mr. Omkar Gaikwad, Associate FE Engineer. On behalf of the Mechanical Department, I would like to welcome you all, and we are honored to have you as our speakers today. Now, it's time for some motivational words from our mentor. I request the Head of Mechanical Department, Dr. Neelaj Deshmukh, to say a few words of wisdom.
Yeah, thank you. Am I audible?
Yes, sir, you are audible.
Yeah, thank you. Good morning, one and all. Today's expert speaker, Mr. Santosh Satre, Senior Engineer CFD, Tenneco Clean Air India Private Limited, Chakan, Pune. Mr. Omkar Gaikwad, Senior Engineer CAE Tenneco Clean Air India Private Limited. Dr. SM Khoth, Principal FCRIT Vashi, Professor Kamlesh, Professor Shoaib, Coordinator of MESA. My fellow staff members and dear students, I welcome you all for Synergy 2021. As MESA, Mechanical Engineering Student Association, every year organizes this event, that Synergy, where the industry institute interaction, where the professionals from industry visit the campus and provide valuable information on different aspects. This type of activity creates awareness among the students about latest advancements in the industry. Synergy helps to establish the relationship with industry and also helps the student for getting internships, final year projects, industrial visit, etc. Till now, many industry visited the campus for Synergy, and for today's program, we have with us Tenneco Clean Air India Private Limited, Pune. I am very much glad today as our ME student, Mr. Santosh Satre, representing Tenneco Clean Air India Private Limited, and interacting with you all. Thank you, Mr. Santosh. Uh, though we are going through a pandemic situation from last 1.5 years, we have successfully completed all academic and extracurricular activities in online mode successfully. I would like to congratulate to all my students for modulating themselves as per the situations and successfully participated in different competitions, completed multiple courses and internships. And we don't know how long we have to conduct all these activities online and what will be the situation in near future. So we should be ready for that. I would like to appeal all of you that you need to do your all activities sincerely and honestly. If you are following this in your life, I'm very much sure that you will definitely achieve success in your professional life. I would like to appreciate the efforts taken by MESA coordinator, Professor Kamlesh, Professor Shoaib, and entire MESA Council for organizing this event. I'm sure that all the students will actively participate in today's event and interact with the experienced professional from Tenneco Clean Air India Private Limited. I wish all the best for today's event. Thank you.
Thank you, sir.
I request our principal, Dr. S.M. Kohl, a man of immense determination and experience, to share his thoughts with us.
Good morning to all. I think today's guest, Dr. Neelaj Deshmukh, Head of the Department of Mechanical Engineering, my fellow faculty members and students. I think this is the era what we are initially discussing. The mechanical engineering always evolved a lot. I think it is your duty to go on even evolving at a faster rate what actually industry needs. The conventionally mechanical was known as what separately design, thermal, manufacturing, and in later stage we went on integrating with what the computer-based concepts, particularly CAD/CAM, and now we are moving one step ahead in terms of what 3D printing. Conventionally, I think some of you, whether you are aware or not, I don't know, because earlier manufacturing was entirely, it is a labor driven activity, and even CNCs were not existing that time. It was simple lathes, shapers, milling machines, and automates, particularly capstan turrets and all, and those are used mainly in industry for manufacturing, and the productivity is always a constant. But from there we went on to special purpose machines or CNCs. So that era, even till now, all those simple machines are disappeared. CNCs are playing a major role, and all those ITI people, particularly machinists and even fitters and all, they used to play a major role in terms of what manufacturing. Now from there, I think we came to where CNCs are majorly used, wherein programming skill was required. Earlier, the operator skill was required to manufacture with more accuracy and all. But later on, it shifted to machines, particularly in terms of what CNCs. And from there, now we are looking at what particularly manufacturing, 3D. And you just think about all what is required. Initially, it was the labor intensive. From there, we shifted to CNCs, whereas machine driven activities. Now, again, we are talking about integration of digital and then physical. So, I can say it is a major breakthrough, and almost only constant, in my opinion, is remained in terms of what cost effectiveness. So already, as far as technology is concerned, it evolved, and already at our doorstep. 3D printing, some of the major parts in automotive, particularly two-wheeler and four-wheeler, already made of 3D printed. Now, even the metal 3D printing is already existing. Now at this particular stage, only issue is cost. If that cost effectiveness comes, because the solar, now we are talking about renewable energy. Earlier, even during my studies, I'm talking about 1988, maybe 32 years back. Even that time also solar energy was existing in terms of what technology, concepts, everything was okay. But it took many years after that to become actually the regular part of what your energy basket. And why it happened? Mainly because of technological breakthrough. And then cost per unit electricity generation through solar is now at par with what even cheapest source of energy generation. You talk about hydroelectricity or even any other source. Now solar energy generation cost is at par with what cheapest source available. And because of that, everywhere you can see that change has already taken place. And now why I'm giving reference of solar energy, because in the similar manner 3D printing is also taking a shape. Now the initial cost of manufacturing is little higher. So once, because of technological breakthrough, the cost comes down, that will become an integral part of what all manufacturing. Now what is the future challenge because of this change of manufacturing strategy? Even your design will change, because when you design your systems, all parts, integral part of what any system as such, there the parts are divided into multiple parts in any system, and that constraints was mainly manufacturing. Even some parts you can cast, some parts you can machine. So those particular constraints are actually coming from manufacturing. Now, if you can print by combining few components together, because there is no constraints of manufacturing, whatever CAD model you can prepare, the same CAD model can be printed, right or not? So those constraints are disappearing. Now, because of this, even the element you are getting, it will be more complex in nature. So your basic theory of design also will change. Now, how technological disruption can affect many things. So one element, we are talking about basic theories. Now, see another story, maybe 30 years back only, the CAD/CAM was actually taking a shape. And that time design in industry was based on making models and analyzing those models in terms of what stress induced and other parameters or deformations or stress induced. I was questioning in one of the seminar myself, how you can teach this particular way of design, because you are not following any basic first principle of designing. Because first principle of design is what? Based on the loads, the cross-sectional area required to sustain that load. But now, if I look into this new trend of manufacturing, and that design will take a central stage. So only basic concepts and fundamentals you should be aware of. Many things are going to change. I think mechanical engineers should ready for those changes, mainly the adaptability. And herein, I think every student, even now, I think you also may be aware of, people talk about artificial intelligence, machine learning, IoT, right or not? All these are existing in mechanical domain, mechanical field. Say you talk about any automotive manufacturers or assembly line, AI is integrated, IoT is integrated. They are already existing, and that existing only in mechanical field. Even talk about your household refrigerators, air conditioners, or even washing machines. The smart systems are existing, isn't it? They control everything. What is that? Already these features are integrated in those products. Now in future we are talking about smart lighting, smart communication devices. When you talk about product, realizable product, mechanical comes in picture. So we need to adapt. I think in 2009, somewhere in the Mumbai University syllabus revision, we introduced automation. Now IT industry is talking about automation now. But in mechanical industry, automation was brought way back, maybe 30 years, 40 years back. So one good thing is all those established practices, good concepts, philosophies. Even now they're talking about agile manufacturing, agile concepts. But agile manufacturing was used in mechanical industry many years. So those concepts are now coming into IT industry. Those are established, well-proven concepts from mechanical fields are taken by IT industry, and they'll be working on that to bring or maybe apply to other domains. Maybe that's good one way, because finally society is benefiting, and the major role of engineers is what? To help society. Huh? Right or not? So in that particular context, you need to think. And what I can say only for mechanical students, you need to change. You need to adapt to whatever changes comes through what technological developments. Because the next 10 years, I feel it will be disruption in many domains. And you need to adapt whatever technology, new technology comes in our way. And as engineers, you need to start working as engineers. And from beginning, I believe mechanical engineering is accommodating many aspects. Why? Because finally, all products realization happens through mechanical. And whatever new technology comes in, if it is advantageous to the society as a whole or product performance, then automatically it will be integrated. As I said, CAD/CAM was not existing earlier. That was integrated very well in mechanical. Similarly, now 3D printing is accommodated. Even automation is accommodated. Now, through the automation, even AI is also integrated. Your IoTs are also integrated. I think you should not run away from the just for the sake of name, artificial intelligence or IoT. I think you people should start learning those and then making effective application in your domain so that your sustainability won't have any problem or any question. I think all new things to be learned and adapted so that your development also may happen more effectively. I think with this particular perspective in mind, we already kept, I think, Python programming in mechanical program at second year level. Even there is a IoT lab for mechanical program. In university also curriculum we are updating regularly. These two new features are already integrated in mechanical curriculum, Python programming and IoT, and artificial intelligence subpart is brought in automation or mechatronic systems. So just think about this. These all changes are now integrated into mechanical core domain also. But what is most important in engineering is understanding energy principles, basic concepts, basic philosophy and fundamentals. I think what my request to all students is go through all those fundamentals and relate to your basic application modes. And you should develop that application capabilities very effectively. So if you can do that, other tools and all you can easily integrate into your systems. With this, I say even today's seminar also, I think CFD is another technology driven system has been adopted, but basic fundamentals are mechanical. So now you can learn even how that can be done by using advanced technologies. If you want to do manually, that may take many hours or many days together. So now that can be solved very easily. But you just need to learn all those aspects, and I believe today's session may help you all to evolve as a better engineers, as a better professionals, and you need to focus on your learning capabilities, and major impact will come only through your self-learning. If you are only dependent on teachers or classroom teaching or examination, you treat your education as only for examination, then you never become an engineer. I think you need to come out of that particular aspect and start thinking about what I learned, what capabilities I developed, what skill sets I developed during these 4 years so that I can build my professional career. That should be your approach. With this, I say this today's session also immensely may benefit all of you. and effectively listen, and then you just try your hand on that particular domain so that you can easily learn. Because it is mainly said, say effectiveness of learning comes only when you do yourself. So learn while doing may be the best philosophy you all supposed to adopt. With this, I wish all the best for this today's session and hope students will immensely benefited. Thank you.
Thank you so much, sir.
Now, we would like to proceed with the appreciation of ex-MESA Council by awarding them certificates for their concerted efforts in the last academic year. With the permission from dignitaries, we would like to proceed with the certificate distribution. First, we have President Chinmay Desai, then Secretary Samantha Dias, Joint Secretary Ruchita Patil, Treasurer Joel Chaco, PRO Melissa David. In the sponsorship committee, we have Mithilesh Dole, Prajwal Umaranikar, Sarthak Barade, and in the magazine committee, we have Zahid Barvelkar, Ruben Pereira, and Vaibhav Mistry.
Urja is the annual magazine of mechanical department in which articles are selected from variety of topics written by students within the domain of our theme. It gives the students exposure and helps them build their knowledge on the topic. The theme of this year's magazine is Robomation, which is basically robotics and automation.
Now, we shall release the most awaited MESA magazine, Urja 2K21, in presence of all the dignitaries. Previous issues of the Urja magazine are available on the Institute website under the Mechanical Engineering tab.
Thank you for being a wonderful audience during the first section of the event. We will now proceed to the second half, which is lined up with the inspiring stories of practical industrial examples.
Now, we will begin with the technical presentations. First up, we have Mr. Santosh Satre to enlighten us with the role of CFD in automotive industry. Mr. Santosh Satre has completed his bachelor's in mechanical engineering and master's in machine design from University of Mumbai. He has worked with Kirloskar Oil Engine, ABL Technical Center India, John Deere, and is currently working as senior engineer in Tenneco Clean Air India Private Limited. Having 9 years of rich experience in CFD, Mr. Satre has always been an enthusiast in exploring domains of CFD and working on prime projects. Now, I request Mr. Santosh Satre to take over and guide us with this presentation.
Yes. Thank you. Thank you all. Thank you to all the MESA team and Synergy team for calling me into this event and letting me share my knowledge and experience here. So I'll try my best to pass whatever my experience and understanding throughout these many years of my industrial experience. Okay, so I'll just share my presentation. Am I audible?
Yes, Santosh.
Yes.
Okay. Is my screen visible?
Yes, Santosh.
Okay. So, mm, again, I would like to say thank you for this invitation. And I think about my organization and background, we have already, the members have already talked about. So I think it's better to directly move on to the main things into the presentation. So my presentation and all this PPT is more consist of the points and questions. So I'll try to verbally explain it. And if you have questions, I think you can ask at the end or even in between is fine for me. Okay, so let's start with some basic but very important question. Importance or advantages of using simulation techniques in industry. The very first or the important question which comes into the mind when we actually enters into industry, how this thing would have been adopted into the industry. Because if you go back to the early industrialization era, we know that everything used to be more like a physical. So even the drawings, even the calculations, and the product development cycle used to be very, you can say, uh, uh, complicated and lengthy at that time, because the main thing into that product development cycle itself is the actual development of the product, and then testing it and approving it to the final manufacturing. And between this, there are multiple cycles of testing being done to verify whether this whatever design is being made is really sustainable or not. So you can imagine that at that time, when there is no simulation thing or no simulation tools available, people used to do more like a hand calculations, and it's more like a guessing the things. So at that time, everything has to go through the testing. And you might assume that, okay, testing, well, what's a big deal into that? They can have multiple testing. They are big industries, millions and billions of dollars they are spending and earning. What is wrong in that? But if you actually, when you will enter into industry, you will come to know that testing is the most costlier and time consuming thing in the industry, for any mechanical industry which develop a mechanical part. Because to develop any part, you need to first develop a die or a tool to make that part, and that initial investment into that tool or die is very huge. And if you want to go into the multiple loops of the testing, you are going to be cost more and more and more. So the most costly thing is going to repeat into your whole process, and that is ultimately going to increase your final cost of the product. Because the prototype is far more costlier than your final series production or mass production product. Mass production is itself says that it's designed for mass producing. So everything is already set, and it's just the repetition of the process. But for proto, before testing, that proto has to go through multiple trials. Because proto, making a proto, then going for testing, then again coming back to proto, what is failed, why it is failed, what modification need to be done, all these things has to happen, and it takes time. When I decide that I have to go for a new die or new tool or uh, a new cast base for some XYZ material, let's say some cone or some shell. So that takes time, and the time and cost involved ultimately gets on building up. So in older days, this all things actually elongate the whole product development cycle. But in between the 1900 era, the numerical methods, our scientist has worked on it, numerical methods developed, and some tools developed which can reflect that numerical method inside it. So once that came into picture, the whole thing, the whole product development cycle started to speeding up. So that speed up and reduction of the cost has increased the speed of the new products coming into the market in shorter duration. So you can even feel that if you go 20 or 30 years back into the time, and if you check how many bikes or car used to come into the market in 1 year, and if you check now how many bikes or cars coming into the market in 1 year, and if you move even back into or 60 years or 90 years back, probably in India we don't have automotive market existing, or not really in that big volume. But if you check the same thing into the European or American market, you will easily understand that the speed of new product coming into the market has really shorted down. So the time has squeezed because of the main thing. I would say that it is the simulation techniques which played a role in reducing the time and cost involved in testing. More and more you go into testing, more the cost and time will involve. Whereas in simulation, you can do the multiple simulation, you can extract much more data, much more in-depth information through that simulation about what is going on, where the critical thing is happening, and you can you can think about the modification, you can do it easily in the CAD, you can implement easily into the simulation tools like into CFD tool or either FEA tool, and you can check its impact. You can keep on moving into that process or the loop until unless you get some sensible results as per your requirement, and that is far more easy and fast process. So this is the real advantage of simulation technique in the industry. But the next question comes: can simulation really replace testing? And the answer is tricky, because uh, though simulation gives us an immense power to cut down our cost and time involved, but ultimately simulation is based on the numerical methods which itself developed based on some assumptions. So it cannot really account each and everything uh, which might happen in real life. So so even in today's scenario, the ultimate approval has to come from the testing. So we can do multiple loops, but at the end, when we decide, okay, this is the best result we are getting into our simulation, and then its prototype is being made, and then it is being tested, and then it is being verified that whether it is really meeting the targets or not. And me being an industrial person, I know that sometimes it happens. Sometimes it happens that your simulation might show good results, but in reality your part fails, and then again you have to repeat the loop, because it happens because uh, it's that you cannot really account each and everything into the simulation. There are some unforeseen situations or unforeseen forces or events that are happening around or inside your system, and which might not really captured into your simulation. And that is why it cannot 100% replace the testing, but it at least replace the loops of the testing. So that is the answer to the second question. And now the third question comes: what different kind of simulation methods nowadays used into industry? So for CFD, it's mainly 1D, 2D, and 3D tools that are available for CFD, where one-dimensional, two-dimensional, and three-dimensional simulations are being carried. One-dimensional, you can understand it just a node to node, whereas two-dimension has XY coordinate, whereas three-dimension has XYZ coordinate. In three-dimension, you involve if it is a transient simulation, you can kind of say it as a 4D, but we generally don't say like that. It's 3D only, but you can do a steady as well as transient simulation. So there are tools like Boost, GT, etc. for the 1D, and for 2D and 3D there are tools like Star CCM, AVL Fire, and Sysfluent, etc. in CFD. Same is for structural. I think structural is more right to comment from Omkar side, because he has good knowledge of it. But they have tools like ANSYS, Abacus, Nastran, Pattern, etc. There is third stream which is being developed or getting focus nowadays is acoustic. Acoustic is more like a 1D simulation, or even they carry 3D simulations for acoustic, but it has altogether a different background and the objectives than CFD and structural. But yes, it do getting a limelight nowadays, because as we know that we as in society, we are going more and more conscious about the things around us, and noise pollution, or the elite feeling behind some noise or behind some tunes are attracting us towards this domain. So this is under development, but not yet really penetrated into the simulation market, at least in India much. Now, if we move ahead, what is about CFD? What is CFD? So yes, bookish definitions we must have read, but I would simply say it like what is CFD? CFD is a virtual testing. Is nothing but a virtual testing which accounts the fluid flow, which accounts the heat and mass transfer, which accounts some physics and chemistry involved into fluid flow. So this is what really the CFD is in simple words. Now, the next question: what basic conservation laws that used to drive the fluid flow, or thereby drive the CFD? So I can expect that you must be, or at least fourth-year student must be knowing it. The very first is the continuity or the conservation of mass. Then second one is the conservation of momentum, and the third one is the conservation of energy. If you go on the higher complexity levels where multi-phase is involved, then there is conservation of species get involved. So these all things are coming into picture when you talk about the basic conservation laws. And now the third question came that which is the pivotal partial differential equation used to describe flow of the fluid and used as a base to develop further simplified and problem specific equations. So I think this also we must be knowing. It is the Navier-Stokes equation. So this is the Navier-Stokes equation, quite big, quite complicated, but you can see that it has the continuity equation into it, the x, y, and z momentum equation into it, and energy equation into it. So this all equation consists altogether makes the Navier-Stokes equation. So after this Navier-Stokes equation, this is the very very initial or very base equation which is used for the CFD. But what are the basic numerical solution methods are being developed out of this Navier-Stokes equation? So if you say the very first solution method is the direct numerical solution. And direct numerical solution, the name suggests, direct numerical solution, it is a direct numerical solution to the Navier-Stokes equation. So you simply try to solve the Navier-Stokes equation. But as you can understand, the Navier-Stokes equation is very basic in its form. So if I have to implement this direct numerical solution method, or use the Navier-Stokes equation as it is into the system, I need to have the much fine discretization of my domain. Discretization is like dividing your CFD domain or CFD volume into multiple small pieces, which is called a cell, and then trying to solve the equation into that cell. But if you are intent to use the direct numerical solution, then you need to have very fine discretization or very small size of the cell, because it try to evaluate every small turbulence, every small eddy into the domain. And it is really it is not a steady thing. It's a transient method, because your eddies or your turbulence, your flow is keep on changing into your domain. So direct numerical solution method is not used commercially. It is used mainly for the you can say academic purpose, research purpose, and it is applied on very small and simple domains, because as I said, it's really complicated to handle it. It needs much bigger resource to resolve the solution, and it needs much more finer discretization. Now the second method is large eddy simulation. This large eddy simulation is nothing but trying to capture, as its name suggests, it's trying to capture the bigger eddies into the domain, because bigger eddies takes more time to dissipate. It has more kinetic energy into it, so it will take more time to dissipate. But the thing about large eddy simulation is that large eddy simulation unable to account the behavior which is happening at the smaller eddy level. So generally, the flow near the surfaces doesn't develop a bigger eddies, but it develops a smaller eddies, and that smaller eddy is not getting accounted in large eddy simulation. So if you need to see the near wall behavior, or if your simulation is more sensitive towards the near wall behavior, then probably large eddy simulation is not the right solution for you. And again, this large eddy simulation needs it's a more like a transient method, and it needs much more resource, that lesser than DNS, but definitely more than other two. Higher resource, mean to say higher computation power, and finer discretization. And the third approach is the RANS, Reynolds average Navier-Stokes equation. So it is the you can say the most simplified form of the Navier-Stokes equation. So there are multiple simplifications being implemented into it. So it is more suitable to have comparatively coarser discretization, and handling a much larger domain of the commercial CFD simulation. So RANS is the numerical solution method, which is mostly used into the industrial domain. Then there is this detached eddy simulation, DES, or also known as the hybrid LES and RANS. So this is sometimes used where your domain is quite big and you are forming bigger eddies, and you need to capture it. So there it is used, and now we'll see the cost versus accuracy of numerical solution method. So DNS, as you say, you can see that on the top of the pyramid, it's DNS, then LES, then hybrid RANS and LES, and then RANS. So the computational cost is high from top to bottom. So mean to say, at the top, DNS has the highest computational cost, but it can resolve the things at very minute level. But more the geometrical complexity increases, its computational cost and time will increase in multifolds. So DNS, then thereafter LES, then hybrid RANS and LES, and then RANS. RANS is at the bottom. It is having the least computational cost, and it can handle the much complex geometries, and it is easy to use. Even you can say on the image on the right hand side, which shows how result can be seen if you implement DNS, then LES, and then RANS. You can easily say that RANS has actually averaged out the behavior of the flow. So in the results where you implement RANS, the result you see is like an average out result. So it's not the real time or the real behavior of the flow. If it is turbulent, it has to be turbulent, and it actually behaves as it is seen in DNS. But it's not commercially feasible, DNS and LES. So we use RANS, and it's like a trade-off between the cost versus you can say complexity. Then there are more turbulence models that are developed under RANS. It is developed because of we try to use or try to resolve the solution in the simulation, which is a phenomena specific or the product specific. So there are K epsilon, K omega, Spallet-Allmaras, then Reynolds strokes or something like that, and there are multiple turbulence models are being developed. But even in this, if you go into the market, the commercial industry is more and more using K epsilon. But as I can tell you, based on my experience, even K epsilon has been evolved to its next level, which refined K epsilon accuracy. So nowadays, it's realizable K epsilon being used into the industry, and there are some industries or the software developers like AVL. They have developed or modified this equation uh, more specific towards the IC engine. So I think they have some KZTIF model. If you can search on internet, you can find it out. KZTIF model, they claim it to be more accurate than a usual K epsilon model. So this development is continuous and it's still going on. So we might see more and more addition into this list. Now, moving to the basic workflow of the CFD simulation. Now this is more into the commercial side or the industrial side, because from point 1 to might be point 7 is the very basic thing. Point 1 to point 7, that is CAD domain selection, CAD cleanup, surface definition, meshing, simulation setup, convergence monitoring, result checking, result extraction, report preparation. Very fine, very basic. But the important thing which I came across into my industrial experience is that this is not the most important thing into the CFD simulation. The most important thing is actually point 0 and point 8. And frankly speaking, without point 0, that is without knowing the objective of the simulation, you cannot actually decide about all these 7 to 8 points. If you don't know the objective of the simulation, you're lost. You're lost about how much CAD domain is to be selected and what kind of surface definitions need to be put it, what kind or level of meshing we need to be put, what simulation setup we have to be using, what conversions we should be monitoring into our simulation, and what kind of result we need to check or extract or put into our report. And then after, how to draw a conclusion, because you don't know the objective of the simulation. I can tell you my own experience that in very initial stage of my career experience, that I have done one exhaust system simulation for the bike engine ATS, and it is not really having a very small catalyst is there, and then there is a muffler, and they have given me CAD model. I have started working on it. I have done meshing, I have done simulation, and yeah, I have started extracting some results, some good cut sections, some visually stunning results. But at the end, when I have to write the this conclusion slide, I got confused, because actually I was not knowing the objective of the simulation. I thought like they wanted to see just the flow behavior into that system. So then I asked the program engineering side guys who are actually dealing between the between us and between the customer. So I asked them, can you just give me the description of the objective of the simulation? And from the SOR, they have given the description. And when I see the description, I just got confused, because that description is actually is just an copied description from another engine, which is having multi-cylinder and multi-port engine. So there they wanted to evaluate how much flow is getting distributed in multiple cylinder, and each cylinder has multiple two ports, two intake ports. So how much distribution is happening within that ports. So that simulation is intended for that objective, and they have just literally taken that objective, copied from there to here, and they intend to draw some percentage of fluid flow distributed from cylinder to cylinder, then within port to port. And I said, like, okay, how can I do this? Because whatever simulation I have carried, it was having just a single port. So there is no question of distribution at all. And ultimately I landed into a report which is not really having any conclusion. It's people say when you when they don't understand the CFD report, or when they don't find CFD report sensible, they called CFD full form as colorful diagrams. It's not computational fluid dynamics, but it's colorful diagrams, because that colorful diagrams doesn't carry any meaning. It's meaningless unless you have a clear objective why you're doing the simulation, and then only you can define from where to where your domain selection has to be, then how your surface definition will go, how your meshing level will go, what kind of simulation setup you will carry, what things you will monitor in convergence, how you'll check the result, how you'll prepare the report, how you'll draw the conclusion. This all things are going to like skeptical. So the most important thing in doing a simulation, or rather I would say, instead of CFD simulation, I would say in any simulation, objective of the simulation carries the highest weightage. You need to understand clearly what is the objective of the simulation, and then you have to decide what has to be carried for the remaining 8 points. So now if we move like CAD domain selection and CAD cleanup. So even in CAD domain selection, as I have already explained the real life incidents which I have experienced, but still, if I say that like in CAD side, what is the role of objective? Then let's say an event where you are analyzing, and again, let's take an example of exhaust system. If you have seen the exhaust system of the car or a truck, then you could see that there is two distinct subsystem into it. One subsystem is actually there to neutralize your emission. One system is there to annotate your noise. So the system which neutralizes the emission is called the hot end. The system which annotate your noise is called as cold end. So let's say if your objective is to check the pressure drop or the back pressure into a cold end. So if you take into simulation, or your CAD engineer by mistakenly give you hot end and cold end both, and if you don't need the objective, you might work on the whole system, and at the end you'll come to know that the time and cost you have involved into the into meshing and simulation in the hot end is actually unnecessary. It is not required, it was not expected. So this kind of events might happen if you don't apply your understanding level while doing the simulation. And under the CAD cleanup, you need to look for this triple or non-manifold edges, then a non-manifold vertex. you can see the image example of non-manifold vertex and non-manifold edges. So non-manifold edges is also called as a triple edge, and it is not expected into the CAD of the CFD, because CFD your surface cannot have an hanging surface. So its non-manifold edge is like an attached extra surface on your main surfaces. So this is the unrequired event. Then there are some free edges, then there are some intersecting surfaces, and then unrealistically small gaps. So these all are the unwanted things, and this need to be resolved. But I can say that these triple or non-manifold edges, non-manifold vertexes, free edges, and intersecting surfaces, these are the things which will not allow itself your meshing to happen. So if these kind of errors are there inside your CAD, cleanup CAD, or the CAD which is used for the final meshing, it's not going to get meshed, because it will not allow you to mesh at all. But for the last point, that is unrealistically small gaps or unwantedly small gaps, that situation it cannot understand, because software is a software. It doesn't have its own intellect to understand whether which small gap is required or important, and which small gap is not required or not important. So that has to be understood by us. And here also I would like to share my own experience in early days, because I have to keep on saying that early days thing, because I have made many mistakes in my early days of my commercial experience. I have done a cooling jacket simulation, CFD simulation, for one of the Indian OEM, and there actually I have taken the geometry, I have carried the simulation, and there are some locations which are showing very abrupt gradients of velocity and pressure, and it's like very difficult to mesh. I have checked it, and I came to know that it has very small thickness. But to understand that thing, it has really taken time for me to understand that thing. And we have already carried some 3-4 iterations on it, and I have given some results or mapping data to the FEA engineers. They have carried some thermal simulations on it, and we have already carried some loops. We have already spent it almost a month or two, and then I come to know that there is something wrong with this geometry. And then I go to a person, I think he's person into the CAD side, and he is an experienced person. So I asked him, like, how this cylinder head and cylinder block is being made. So he said, generally by casting. So okay, so generally by casting. So how much minimum casting thickness can be achieved? So he said, if your casting thickness is less than 6 mm, and it might happen that in real time event, while you pour your cast with the molten metal, your metal may not reach to the location where the gap is less than 6 mm. And in reality, you will not see any metal there. So I came to know the reason behind the abrupt results, because the location what I am looking the abrupt results at is actually having a thickness of less than 1 mm, and in reality it is not possible. So that time I came to know that such things might get slipped from designer. But being an CFD engineer, we have to be alert and we have to check for such kind of unnecessary or wrong things into our simulation. That some unrealistic gaps we have to understand it, analyze it, and if we required, remove it. So this is in the CAD side. Then surface definition. So once our CAD has been cleaned, we have to define our surfaces, like define our boundaries for the surfaces. So mainly where the flow is coming in and going out, there has to be an inlet and outlet boundary. And for the surfaces which is not playing any role into inlet outlet boundaries, they have to be defined as wall. But there are some simulations like sloshing simulation or the splashing simulation, where there is generally no inlet outlet, but in wall boundaries you define almost all the things in there. So within inlet you can define either mass flow or velocity or pressure, etc. In outlet you can define mass flow, pressure, etc. But you need to understand this thing, that inlet and outlet are very key things. So there are some feasible and unfeasible combinations in the inlet outlet. So you cannot simply apply uh, mass flow at the inlet and mass flow at the outlet, or velocity at the outlet, because uh, the background of the or the equations which is being calculated or resolved at the back end doesn't allow some combinations to happen. Or if you apply that kind of combinations, it might give you either wrong results or it might diverge your simulation. It will not converge. So you need to understand such kind of combinations, which are favorable or feasible combinations, and some are unfavorable and unfeasible combinations in the inlet and outlet. So this is again an kind of looked into an industrial experience. Then there is a wall boundary. In wall boundary, you define heat transfer, whether it is no heat transfer at all, like adiabatic condition, or it is having some conduction, convection, radiation. Then you can also define symmetry. Far field symmetry is generally used when you have a domain which is symmetric at certain axis or certain plane. Then far field is a boundary condition where you try to replicate a much bigger environment. So and there are many more into it. So even as per the tool, this number of definitions could get changed. So let's move to the next point. Then there is a meshing, and inside a meshing, the very first or the important things comes into picture is cell type. So here what I showed is the two-dimensional thing. It is actually two-dimensional, or the surface mesh is inside the CAD and mesh definition. So this comes into picture inside CAD and mesh definition. When you get a CAD model from CAD engineer, either in the CAD part format, or in .stp format, or .stl format, or .igs format, you need to see you'll see that it's generally a triangulated model. So it gets a discretization of that surface in triangulation form. Or in a very rare case, you might see this quadrangle, but I haven't seen this anywhere until my experience till now. It's mostly the triangle one, and when you convert it into a 3D simulation mesh, it becomes all volumes. So there is a tetrahedron, or we in short call is as tetra mesh. Then there is a hexahedron mesh. Then there is a pyramidal or wedge kind of mesh. So I think almost 10-15 years back, the CFD tool and CFD industry used to think like hexahedron is the most you can say most favorable or most accurate cell type to be used in the CFD domain. But over time, because as much I remember, at the early stage of my commercial experience, at that time, ANSYS Fluent used to use this tetra mesh, whereas AVL Fire used to have this hexa dominant mesh. Then this Star CCM has already using a polyhedral mesh, the image which is on the downside, and over a time it's being understand that using a pure tetrahedron mesh somewhat compromises your accuracy. Hexahedron mesh is good for the accuracy, but the thing is still the hexahedron mesh is creating an issue while meshing is happening, because it has a definite shape, and it generally gives you many errors after a mesh, and you have to work more into the meshing. I have experienced it. So it used to be complicated and slightly time consuming, that you might need to go for 2-3 iterations to achieve a good quality mesh with the hexadominant mesher. And I think in hexadominant mesher itself, to accommodate transition of the mesh size, this pyramid and wedge cells are being used. But over a time, in this all 9-10 years, I have seen that the whole CFD industry is already trying to move into poly direction. So this polyhedral mesh is much easier to use, and it gives very comparatively very less errors, and it has a decent accuracy level, because the the shape itself is not definite, and it can have multiple faces, so more than hexahedron. But how much multiple, there is no definition like that. So you can have like in hexa there are 6 faces, you can have 8, 10, 12 to accommodate into the domain. It can change its number of faces, it can change its shape, size. So it's very flexible. So you get very less errors in there, much easier to use, much faster to work with. Because in hexahedron, if you have some issue inside meshing, the mesh itself, the mesher tool itself goes into multiple loops to resolve that localized error, or to accommodate a cell into that particular domain. So poly nowadays are being adopted by most of the software developers. Even there is one new methodology which is coming into picture, called as an adaptive mesh or meshless CFD simulation, which is actually not really a meshless thing, but that mesh itself gets adapted as per the flow. I don't know how much is its feasibility, but I can just tell based on my industrial discussions that this meshless kind of thing is coming into picture. Then there are some software developers who has trying to overcome this limitation of hexaedral mesh. So they adopted an hanging node kind of mesh where your hexahedron can just move to any size, or rather from single mesh to single cell to two cell, and there is one node which is not connected to anywhere, and it is hanging. So that kind of research is already going on, and you might see, if you go into CFD domain, you might see something different than what I'm doing right now. Okay. So inside meshing, there is importance of this surface refinement and volume refinement. Again, this is more to do with the objective of your simulation and the complexity of your CAD. So let's say you want to see, or you want to capture the near wall behavior, because it is more to do with the results you want to see. Like here you can see that on that truck, it's under hood simulation, and it's a cut section of the mesh. So you can clearly see that the near the truck surface, that dark black, then do two layers of light black. They are surface refinements with some depth definition into it. But the after that, you can clearly see that there is a proper box shape. I think 1, 2, 3 you can see, and that is actually a volumetric refinement. You have defined a proper volume, and now you have given a cell size which is to be applied into that volume. You have defined surface, you have defined depth, and you have defined the mesh refinement level. So this has to be also connect with the level of accuracy or in depth of results you need into your simulation. So objective plays a key role here also. Then inside meshing, again, there are type of mesh. So like there is a static mesh, that is a single mesh which will be used throughout your simulation, whereas there is another mesh type which is a morphing mesh, which is an actual mesh moment or stretching or squeezing happening inside mesh. So this static is generally used where your domain is constant, and morphing mesh, you can imagine this in-cylinder simulation. So in in-cylinder simulation, your piston is moving, so you have to accommodate that moment. So you have to define that multiple instances of mesh. So for that particular crank angle, that mesh will created and will either squeeze or stretch up to that crank angle, and after that again it will go into the new mesh, squeeze or stretch. So that is a mesh morphing. The third one, this MRF, moving reference frame, is not really a type of mesh, but it's an simulation methodology, but it has to has its reflection into mesh also. So I have written it here. Then there is a mesh quality check which need to be carried into this meshing. Again here, mainly the negative volume, then orthogonality, aspect ratio, etc., etc. You can see this. These names might be different in different tools, but here I can say that this negative volume It's you can clearly imagine what is a good quality mesh or good quality cell is a cell which is having a consistent size and shape. So that is the basic criteria. So when I say negative volume pertains to a situation where your mesh is so much distorted or your cell is so much distorted that your CG of the cell, center of the gravity of the cell, is actually coming out of the cell or outside your cell. So that is like a no-go event. So if you have a negative volume cell into your CFD domain mesh, no, simulation is not going to happen at all. But orthogonality, or this orthogonality can have different name in other software, but this orthogonality is like how much distortion happened into cell. So there is some limit to this. If it is within that limit, it's okay, it will not show any problem. If it is out of the limit, or if your simulation is a bit complicated, high turbulence, high velocity, high mass flow rate, high temperature, then you need to follow some stringent guideline for the orthogonality. And if you don't, then your simulation might get destabilized or might give you some error, some results. So even the aspect ratio, generally not really a stringent, you can say stringent constraint, but sometimes if it aspect ratio is like you can say length to width ratio. So if it gets too much big, then it creates a problem, because then the solution which is being you can say which is being transported from cell to cell, cell center to cell center, it has to go through an upgradation from cell center to cell center based on the distance. If the distance is too big, then the upgradation is difficult to happen, and it gives then error or destabilize your simulation. So that is the thing. Then there is one very important thing which I again say that based on my experience, that mesh independent simulation, lot many people use that word, or rather I would say it's the word which is more used into the academic side of the CFD. Mesh independent simulation. What is it actually? Mesh independent simulation says that your mesh, it has to be such that it has to be such that it will not show or change into the flow domain or the results, if even if you change a mesh, or even if you refine mesh below that certain level. So based on my experience, I have to say that I have to pose a question whether it is reality, whether it is myth, or whether it is a trade-off. Because in reality, in industrial problems, you cannot keep on doing this practice again and again to check whether your mesh is really changing the simulation. Let's say if I'm discretizing my domain with the cell size of 8 mm or 10 mm, then I simulate it, I check the result, then I go for the size of 6 mm. I done the mesh, done the simulation, check the results, then I go for 4 mm, then I go for 1 mm. And my experience says that as you keep on changing this, you are going to have experience of you are going to experience that results are more or less getting changed. It is altering the flow domain, how your flow domain is looking like, how the results or the flow inside or pressure inside a domain is looking like. But the thing is it reality? I think it's difficult. At least for commercial problems, for academic problems, you might have a time, you might do that practice again and again. But in commercial, I think it's really stringent timelines, and you cannot keep on doing this thing every time. So for commercial life or for commercial CFD simulation, it's not really a reality. But is it a myth? No, it's not really a myth too, because you cannot take an advantage of saying, oh, I want to I want to I want to have a simulation, or I want to have a results in very short of time. So I have taken a very coarse mesh. No, you can't do that. Excessively coarse mesh will going to alter your result so much that you cannot say it to be an relevant result at all. So it's really actually in commercial life, if you are a CFD engineer or simulation engineer, it's mesh independent simulation is actually a trade-off. It's a trade-off between the time and resource involved into the simulation due to finer mesh versus uh, using a coarser mesh to save your time and cost, but not really compromising too much on your accuracy side. So generally, based on our experience, we try to find out cell sizes which gives us an optimized cell count at the end, which is easy to use or optimized in time consuming side, but which do not compromise much on the accuracy side of the results. So it is really a trade-off. It's not really a myth, not really a hardcore reality, but it is a trade-off. Mesh independent simulation. Then simulation setup. So inside a simulation setup, there are domain phases which need to be defined, like either it is fluid, so CFD है तो fluid तो होगा ही. So fluid has to be there. But let's say you have to have some simulation where fluid solid interaction, either heat transfer or any Wolfram phenomena has going to take place, then you have to involve the solid phase also. Then either you have to, if you have something like let's say exhaust after treatment system where the catalysts are there, which is defined as a porous or radiator system, which is where it's very difficult to simulate the fins, which are very thin and multiple in numbers. So they generally model it as a porous domain. So based on your simulation requirement and what is involved into your simulation, you have to choose between the remaining two phases, solid or porous. Then there are fluid types. So fluid, either gas or liquid. Then there is phase, either it's a single phase or multi-phase. Let's say if it is a multi-phase, then what kind of approach you are going to take, either Lagrangian approach or Eulerian or a lump mass approach. So generally Lagrangian approach is taken where your base one fluid is very ample into a quantity and volume as compared to the other fluid, like a situation of a fuel injection in combustion chamber. So the volume of fuel as compared to the volume of the whole combustion chamber is very less, probably in 1% or less than that. So in that situation, you can simply go for a Lagrangian approach. But Eulerian or lump mass approach is carried where your code domain has considerable volume into a domain, like say 10%, 20%, 30% of the gas and remaining 70% of the fluid. So that in that situation you need to go for a lump mass approach or Eulerian approach. So that is a situation in sloshing or splashing kind of simulation, CFD simulation. Then there are some additional phenomenon based on your kind of simulation or kind of objectives you want to implement. So you might need to implement a gravity or Bosix model. Then you might need to implement a boiling model. You might need to implement a wall film model if there is some some injection or something like that. Like say we used to implement a gravity or boiling model sometimes into our cooling jacket simulation, because there are some cases where this boiling phenomena might occur, and there are some places where you have a stagnant fluid, and due to gravity you might see some flow in that stagnant region. Or even this wall film is generally used in our in-cylinder simulation, in-cylinder or combustion simulation, or even this SCR simulation, ATS simulation, where some fluid is being injected, and that fluid might hit some surface and might create some wall film there. So to account that kind of phenomena, this additional models need to get included into your simulation. So again, here also you can see that your basic objective of the simulation is playing a role into your selection of the models. Then the convergence monitoring. So convergence monitoring is like a thing by which you can understand whether your simulation is behaving correctly or in right direction, whether there is something wrong into your simulation, either on meshing side or either on setup side. So I can tell you in my own experience that in my initial days I used to experience that my simulation don't used to converge easily, and I used to get confused that what is wrong. So generally I used to go for the go to the mesh, recheck the quality, and sometime I came to know that okay, there are some cells which are bad cells and need to be repaired. So I go either for remeshing or node movement to improve that mesh quality. Sometimes I came to know that in my boundary condition I have done some mistakes, and I have applied some abrupt boundaries. So in that case also either boundaries or either in initial condition. So in that case also I used to came to know it from the convergence monitors or convergence plots I have set up. So it is again an important thing how what you want to look for as in your convergence criteria. So generally it's the residual plot, which is the basic thing, which is actually show you the like what I said as the continuity equation, XYZ momentum and energy. So other than that, it also shows you the turbulence kinetic energy trend line, then turbulence dissipation rate trend line. So from that plot, and if you add some more models into simulation setup, then you might see some more things into your residual plot. but it is very basic plot, and from that you might not really know that whether it is sufficient on the side of saying that convergence is really happening. So so in that you can say we can put a residual or mass flow, temperature, pressure, uniformity index, solid surface temperatures, minimum maximum domain. So it's all depend on what kind of simulation you are doing or what kind of objective you are having in front of you. So this is about convergence monitoring. Then there is some result checking, result extraction. Again, here you can have some cut sections for the flow, pressure, temperatures. You can look for the streamlines. You can look for the uniformity index sections, species fraction, wall frame, etc., etc. Again, depends on what kind of objective you are having into your simulation. So by this also you might experience that you're from the plots. It rarely happens, but it might happen. It do happens with me sometimes that I see everything went right into the convergence plot, but when I go into the 3D results, check the cut sections or the streamlines or something like that, I see something wrong somewhere. It rarely happens, but it might happen. So you need to check that also. Then I would like to talk about this also, that at the end from the results you have to draw a conclusion and give a suggesting an improvement modification. So this is the really crux or the important thing of the CFD simulation, where your technical as well as analytical understanding comes into picture, and you need to understand again the constraints when you give and suggest improvement modification suggestion. Because I do remember again back into my early phase of commercial life or as an CFD engineer, that I used to give some extraordinary modification suggestion, but that suggestion used to get rejected from the CAD or manufacturing side, and they used to say, okay, this is not feasible, this is not cost effective, this is not good in this is not good, or this is not acceptable in packaging point of view. So actually there are multiple aspects which you need to take into account while giving an improvement suggestion modifications, uh, whether it is going to get manufactured or not, and if it is going to get manufactured, whether the cost of manufacturing involved is feasible or not for considering the overall cost of the product. Then the second question, whether its assembly is possible or not, whether it is going to get properly assembled with its main system, parent system or not. Because sometimes it might happen that the suggestion which we give, it's difficult to implement because it's not going to get assembled properly with our parent system. So such suggestions cannot be implemented. Then third is you need to consider the peripherals of the system, because in let's say in IC engine, you know that around engine, in that engine cabin, there are multiple things and multiple subsystems existing around that engine. So you have very limited space for everything. So you cannot just give suggestions something which is going to alter alter another system's position or size or shape. So that is also not really a feasible way of doing it. So you need to account this thing while giving the suggestion, and you need to have a global perspective while suggesting an improvement modification. So these are the main things, and now I would just like to say that what kind of different type of CFD simulations being carried in automotive industry. So if I say about automotive industry, let's say which is like okay. So it's intake system, then intake port, in cylinder or combustion simulation, piston cooling or oil splashing simulation, turbocharger flow, exhaust ATS, external or underhood simulations. So these are all are generally carried in 3D domain, and it is related with the internal combustion engine. But this in cylinder or combustion simulation, you might experience also in 2D domain. And then there are some simulations which are common into internal combustion engine and EV also. So there is a cooling unit or cooling jacket which is there in both IC engine and EV, and it is generally a 3D simulation. Then there is a radiator cooling, which is again uh, similar or not really similar, but identical in IC engine and electric vehicle. Then air conditioning unit, then cabin cooling. So these all these four are like identical in both IC engine and electric vehicle. Then in 1D CFD simulation, all the above mentioned simulation can be carried either individually or all together as a single system, altogether a single system. But 1D simulation, 1D CFD simulation is more into a system simulation. So it tries to get involved all the or the maximum of the systems at a time into the simulation, so they can have a global perspective of what will happen throughout the system. So that is what the 1D is more preferred for. So I think from time side, I think I have already exceeded my time. So I think I'll move to the more to the conclusion side. So after hearing all this, or after studying the CFD, if you feel that you have some alignment or some attraction towards becoming a CFD engineer, then what you should be doing? You should be BTech final year, your B or BTech or ME or MTech final year project, a full-time project. You should be doing in CFD. That's what I have done. I went to Kirloskar Oil Engine, and there I have done my ME final year project, full-time project. I was there for almost 8-9 months. And based on that experience only, AVL selected me as a CFD analyst. So either you do it this way, or you can join an institute which can teach you CFD, as well as can able to give you an on-job training for CFD, either as a third-party engineer or taking some pilot projects from some industry. So it's Skilling or some Optimist Technology. These are some names I have heard which can do that. So these are the two things. But other than that, in reality, actually building a good technical and analytical skill is very much required to be a good CFD engineer. A good CFD engineer is the one who understands the simulation objective and simulation results properly, give more inclusive and feasible improvement modification suggestion, and who can able to read and understand things between the lines. So this third point is, it will take a time to develop, because you might experience that it's not the only thing which you see on your screen that is taking a place in reality. But if you try to understand what is really happening in there, or try to analyze it, then you can better able to read your results, what you see on your screen, and then you can give more precise suggestions or more precise comments about the system. So this is from my side, and at the end, I want to say thank you again for calling me here and bearing me for this almost 1.5 hours. Thank you to the FCRIT, the team, the mechanical engineer, the group, MESA, and Synergy team. And I want to express my gratitude towards mainly the Father Agnell College and Coach Sir, who actually shaped the initial phase of my career. And he was a mentor my guide for my project in my ME second year. And yes, definitely at that time, the rest of the staff, Nilad sir, then Yevle sir, then Chaudhary sir, Aklim sir, so they all were kind of involved directly and indirectly in shaping my early phase of my career. And even then after, whoever people directly or indirectly involved in shaping my career. Thank you from my side. So I think if you want to go for a Q&A session, we can.
Thank you, sir, for your illuminating presentation and letting us know the importance of knowing the objective of simulation being done. As you have said, without the objective, computational fluid dynamics turns out to be colorful diagrams. We will definitely remember this experience of yours of knowing the objective and working under it. We are open for questions. Please raise your hand if you have any doubts. So we can unmute you and you can ask the question.
I hope I haven't bored you people so much so that you just went into sleep or hibernation. Or it is really enlightening that you cannot ask a question.
So if you have any questions, please raise your hands.
Do we have already learned this fluid and mass transfer? Sorry, fluid mechanics and heat and mass transfer in our third and fourth year?
Yes,
so
sir,
there are third and fourth year guys, right?
As well as second year students also.
Okay. So I think I can expect some questions from you guys, at least fourth year guys. Though I am not really remember much of the basic things from my academics, but I'll try.
Hello, sir.
Yes.
Sir, can I ask a question?
Yeah, please.
Sir, for the big projects like NASA's and ISRO's for rocket project and engine testing and simulation, do they go with simulation or testing?
Yes, I think this is a relevant question. As I said, that testing is the final approver, but there are some situations where it's difficult to test at all. So you cannot really create like a proto model of rocket and send it to the outside the gravity of Earth. And oh, that's okay, that's cool, good, okay, come back and now we'll send a real model. That cannot be a sensible thing to do. So in that cases, yes, they have to rely more on to simulation or you can say testing of subsystems, not a complete system, not really really launching a proto model of the rocket. But they have to, like, say, where the industry runs more into a drive more from cost side. So if your cost involved is too much, then precautions taken for system not to get fail will also be too much. So whatever simulation they will carry, whatever testing they will carry, will be definitely very, very stringent, with very, very stringent objectives and parameters. So then only they can rely on it, and then they can spend that much of money to directly prepare a final model and send it into space. So there you can say that it's partially a simulation and partially a subsystem testing, uh, which is not really a full system testing. So not possible there, really.
Yes, sir. Thank you. So I have another question.
Yeah.
So for car safety testing, can we rely on simulation for safety check of car? Because mostly for to check the safety of car, they do tests, they crash testings and safety testings. But can we use simulations rather than testing?
Yes, it's very general practice. They have crash test simulation at their end, and they use it to reach to an final model where they can say that now our car is safe. They see OEM or the final car manufacturer can have their own test of crash, but whether it is really relevant or equivalent to some international independent test is to be thought by OEM only. But if you say yes, that crash test does happen, and I think this is in on structural side. So Omkar could add something into this answer into his session if he wants.
Yeah, definitely.
So I hope sir has answered your question. Are there any more questions? Okay, there are no more. Yes, Siddharth Kannadkar. Yes.
Sir, are there any career opportunities for CFD engineer in India at present?
Yes, lot many. Actually, frankly speaking, simulation side is not yet that much saturated with the head count as much it is saturated in design side. So generally, mechanical engineers generally go either into design or either into simulation. But simulation side is not yet that much saturated as it is saturated for design, because going into design is far more simple than to go into a simulation. Simulation needs more better and in-depth analytical understanding. So definitely simulation, and in that I would say particularly CFD or particularly uh, some domains, subdomains into FEA still has not that much of headcount. So it's not yet fully saturated. So you can think of going for it. There are in India there are good opportunities also, because in India you can understand that due to cost effectiveness of the workforce, lot many OEMs, lot many outside industries are building their technical centers here, and we are technically sound, or technically sound as well as cost effective workforce, so they have some alignment towards us. So it's still building up, and due to this pandemic situation, there is more chances that more and more companies will try to set up their technical centers here into India to save their cost, and it is going to increase the opportunities in coming future. So definitely you are going to feel less struggle or less competition in simulation as compared to design in future. I'm not underestimating design. Let me clarify. Yeah, someone else want to ask?
Good morning, sir. Sir, I wanted to ask that in the beginning, when you told us about the different turbulence methods, like K omega, K epsilon, so what is the basic criteria to select one when working on a particular model?
Okay, I would say this is more like an academic question, but still I'll answer that. It's like what kind of flow behavior is happening into your domain is the main criteria stands to select that models, turbulence models. Let's say this K epsilon model is actually initially K omega model was developed, but it was the accuracy level was not that good. Then K epsilon model get developed, and accuracy level is increased, and then furthermore to increase the accuracy level, so this K omega or K epsilon models are working, or they work more accurately for closed domains, smaller and closed domains. But if you think of a big and open domain, or you want to simulate a fuselage, a flow or a fuselage, or flow over a aeroplane, you can say that hands aeroplane. For that they use this the third model, Spallard Almaraz. They could use that model because the design of that model, the assumptions taken at the base of that model is like there will be almost no or minimum flow separation happening inside the fluid domain. So over a fuselage, you see that flow smoothly enters into your on your blade, and then smoothly exits on your blade. So there is hardly any flow separation happening there. So that for that kind of case, that thing is good. But if you apply this K epsilon or K omega model there, then you might not get the accurate result. But if you apply this Palette Almaraz model here in the normal domain, like underhood simulation, or like where there is a quite good amount of flow separation bound to happen, then it may give some abrupt results. So it's more towards what possibly going to happen into your domain. So that is going to drive your selection of the turbulence model.
Thank you, sir.
Next, we have Jayesh.
Hello, sir. I wanted to ask what are the major parameters or parameters of concern when we shift from hydrodynamic analysis to aerodynamic? Like means Reynolds number means which should be the prime focus that it's important when we shift.
Can you explain me a bit? Hydrodynamic analysis mean to say what kind of
Sir, in
analysis?
case of like ships and when we do analysis, and in case of
Okay.
aeroplanes, when we do analysis, like means the fluid is different, right? So
Yes.
which parameters we should keep in mind, like Reynolds number or what, sir? Means what should be the major
Okay. Okay.
concern?
Okay. Okay. Right. I understand. Okay. First thing I would like to tell you from my own experience that even though this Reynolds number, Nusselt's number, Prandtl number, these all are very important numbers, which is actually in the base of the fluid dynamics, even in the base of the computational fluid dynamics. But I have experience in my industrial practice. Probably that can be my personal experience, may not be everyone's.
Hello.
Santosh, I think we lost you actually.
Hello, I guess sir is having some network issue. So if you have any questions, you can ask at the end. Now, I would like Aditi to introduce the next speaker.
Thank you, Prabhu. Next up, we have Mr. Omkar Gaikwad. Mr. Omkar Gaikwad currently works in the automotive domain as an associate FEA engineer in Tenneco Clean Air India Private Limited. He has completed his bachelor's in mechanical engineering from HSIT, Vishveshwaraya Technological University, Belgaum. Having more than 6 years of experience in FEA and durability, Mr. Omkar Gaikwad is an expert in analyzing automotive exhaust systems for light vehicles, commercial vehicles, and off-highway vehicles. Today, he will be guiding us about the role of structural simulation in the automotive industry. I request Mr. Omkar Gaikwad to proceed with the presentation.
Hello.
Oh yeah. Good morning, all. I think it's 10:50, 11:54. Okay, still it's depend on the weather.
Sorry, Omkar, I muted you.
Are you able to hear me?
Yes, yes.
Yes, sir.
Yes, sir.
Okay. So yeah, good morning, everyone. So I think we'll directly jump to the presentation. And here we go. So are you able to see? Oh.
Yes, sir.
Yes, sir.
So today, I think besides the FEA, I'm going to do some things on the SVNR as well. So SVNR is another department in all the organization, but it's not known to everyone because it's we can say not all the OEMs are following this, or I think only OEMs are following this. Not all the tier 1s and tier 2 suppliers are doing this on these things. So SVNR is basically the system validation and research team. So where all the things all the teams are going to be interpreted. So it's like purchasing, marketing, sales, and DVP. That is like design validation planning and reporting, that all the teams are in the one system, that is a system validation and requirement team. So we have that Rasik which tell us who is going to do the purchasing, who is going to do the marketing, who is going to do the sales, and who is going to do the DVP things. So uh, all the requirements and all other, I can say, responsibilities are defined over here, so no one can interrupt it into each other's domain. There are some links who can interrupt it, but those are mentioned in the RASIC only. So this is something which is very essential in the OEM, and this has been followed by all the OEMs as well as some of the tier 1 suppliers. So if you're going to buy anything, there should be something like you will ask for the how much life of the product, or how much output it can give, and how much time it will give. If you want to buy a product, like if you want to buy a mobile, you will ask for them like how much the warranty for this, how much the warranty for the headphones. Hope my screen is visible, right?
Yes.
Yeah. So for that, any OEM or any company will make the SOR, that is like a statement of the requirement. So they will say it should survive for 1 year, it should survive for this much time, or it should survive within this limit, or it should survive with these conditions, and it should give this much output. So they will make this SOR and circulate to the OEM. So that things is a management thing. So management thing will do the SOR, and they will provide it to the tier 1 or the internal development team. So say suppose we are making the mobile, and they told us like it should survive for the 1 year. So all the components in that mobile should survive for 1 year. So it's depend on the camera, it's not on the all the components. So all the components should survive for the 1 year. So the OEMs are not making the camera and all, so they have taken it from the tier 1 or tier 2 supplier. Tier 1 are like the suppliers who are directly supplying their equipment to the OEM. OEM is basically original equipment manufacturer. So they are providing the tier 1 are supplying directly to OEM, tier 2 are supplying to tier 1, and they are providing that to the OEM. So this is how the SOR works. So SOR is a statement of requirement. This had been made by the OEMs, and this has been circulated to OEM, to internal team, or to the tier 1 suppliers. And all the requirement over there should be fulfilled by the suppliers or the internal team. Next topic is the DVP. So what is the DVP? So design validation plan. So if you are making any design, there should be something like a design validation plan. You're not going to directly make the design and going to submit it, and it should be some process. Okay, so for this process there is a two department. First one is the RFQ, and second one is the development. So first one is RFQ. As RFQ is a when you get any product, like say suppose there are 10 vendors and Maruti Suzuki want to develop one product from you. So they will send this SOR to all 10 vendors and tell them to pass in their criteria. So they will test it only on the design at that stage. And when they get nominated, then it will move to the development phase. So there are two phases over there. One is RFQ, second one is development. In the RFQ stage, you will only evaluate on the design basis. So in the design, you will have CAD, CFD, and FEA, as well as acoustic will be there. So all these things will be evaluated in the RFQ stage. And when it will went to the development stage, the testing and measurement will be done. But as Santosh has mentioned, in the development, they will test it not only on the line product, they will first test it on the proto product, because this is easier to make, and this is it is not time consuming. So that they will make it on the proto things, and then they will move it to the line product. So at the development stage, they will test it twice, but in the RFQ stage, they will test this. They will do the evaluation at the one time only. So first they will do the 2D drawing and convert that 2D drawing to 3D drawing. That will be the CAD model. with Katia, Creo, and all the software like Sortilege, they will work on, and then the CFD will happen, the flow simulation. After the green signal from the flow simulation, the durability will happen, the FA will happen, and after, if it is passed from the durability, the acoustic will be happen parallelly. So this is something from the SVNR team. So this is like very short department, and in this department, the very experienced person will work. Like if you are having 10 years of experience in one company only, then this person will adopt it as a SVN person, because you should have very basic knowledge and very detailed knowledge of the product. Then only you can work on this field, because you need to sign all the DVP and SVNR plans. So in that statement, if you are working with any OEM, and if you are a tier 1 supplier, and if you are signing those documents, okay, this is criteria, passing the criteria from the CAD, from the CFD, from the FA, and from the testing as well, then you will be the responsible for the product. So if it's not surviving for the 10 million cycles, or say suppose for the 5 years, then you will be responsible for that product. So this is the one of the like tricky, or one of the main department where all the experienced person of that company only will work. If you're having 20 years of experience with 6 companies, it will not be calculated. If you should have like decades of experience in that same company, then only this SVR manager will be, you are allocated as this SVR person. So there are also like branches in the SVR. So you can become the SVR purchasing person, marketing person, sales person, and SVR DVP person. So this is like sub branches of this. So I think this is something which is new for you as well. This SVR department. Anyone heard about this before? Okay, I think no one has heard about this before. Anything you need to ask in the SVR, how it works and how it goes and who defines the criteria? Okay. So we will jump to the FEA. So I think, okay, it's clear. FEA is a finite element analysis. So do you know why it is called as FEA, or why it is called as a CE? Okay, so say suppose you have screen in front of you, so you need to like check the screen, or you need to give the definition of that screen. So it should be in the infinite particles now, like it's shown here. So there are like n numbers of points, and each point is contain 6 degrees of freedom. So each equation is like infinity. So convert those infinity to the finite. We do the infinite, or like finite element analysis. So this is like, we had divided this into now 8 nodes. This is like one node, 1, 2, 3, 4, 5, 6, 7, 8. So all the points which are here are in the terms of the FEA are called as a node. So these are the nodes 1, 2, 3, 4, 5, 6, 7, 8. So these are nodes, and each node will contain this like 6 degrees of freedom. So there will be the 48 equations we will going to proceed with. So all the points in the terms of the FEA are called as a node, and all these small volumes in terms of the FEA are called as an element. So these are the node and elements. Okay. So okay, so this is something which we do in the FEA. The first thing we do is a pre-processing, that is a FEA modeling. The second thing we do is an analysis, that is like solution of the product. And third thing we do is a post-processing, that is like reporting and more of like stress plots and all. So in the FEA modeling, are you aware about the 3D modeling? Like, are you aware the CAD geometries and all? Okay. So, like, any one of you have used the CAD modeling tools? Any one of you? So, which one you are using in your academics?
Inventor and Fusion 360.
Okay, and what is like outcome of that? In which format it will come? Surface, solid?
Solid.
Solid, okay. So we will, for the durability purpose, we will require the model in solid format only. So first, when we get any model in the solid format, we'll do some cleanup over there. Then we will split the solid and make into the meshing format. And the last thing which we do is the meshing checking, where all the OEMs have their standard meshing quality checks, and we passes those criteria, and then only it should be proceed for the analysis. So say suppose your elements are distorted. Say suppose you have these elements which look good, but if you have distorted these elements and it is not passing the criteria, you will not get a relevant solution for this. So it should passes all the criteria. So meshing is split in between these few points. Like meshing, we can do, if it is 1D, we can do it with the rod or beam. So how you will define the 1D? Like how you will define the 1D? The definition of 1D? Any one of you?
Are there surface elements that are typically made with triangles or quadrilaterals, like basic shapes?
Define the 1D like quadrilateral.
Sir, all the properties are only in the one dimension.
Yeah, exactly. This is my point. This is where I come near, like you guys will come to. Okay, so this is like only two-dimensional, are like only one-dimensional is more than two-dimensional in the 1D, right? And in the 2D, the third dimensional will be not that much significant, as you can see in the sheet metal plates. And the 3D, all the components are there, all the planes are there in the XYZ, all the planes are there. And so 1D will be mostly the rods and beam, 2D mostly will be sheet metals, and 3D mostly the casting components and foams. And there's one more term in the FEA, that is 0D. So 0D is like a CG of the component as a node mass. So if you have the human being, so you don't need to model this human being. You just can take the CG of this human being, and you can model these two legs with the help of special elements such as RB2 or RB3 elements. These are beam elements, and you can consider, where is my point? Okay. You can consider these legs as a resting point for this beam element, and you can directly apply the mass over here. So suppose this is having 70 kg, so you can directly apply 70 kg on this node, and with help of the two RB2 elements, you can directly convert this mass on these resting points. So this is something which is we do in the FEA. If some components are not essential to model, we'll convert those component into the CG, and with where they are resting, those points will be taken care for the RB2 or RB3 elements. So that this point will directly transfer the load on these 2 points. This is like elaborating the elements. So 1D we have, 2D we have, 3D we have, and other elements such as mass, spring, damper, gap, and this 3G element, which are there for the mass elements. These are there. So 1D is, as you said, like one dimension, two-dimensional in 2D, and three-dimensional, all the dimensional is XYZ plane. So all are near to each other. So in 1D, we use beam elements and bar elements. So in 2D, we use quad, tria elements. In 3D, we use penta and hexa elements. and in the other elements such as mass is like con-m, RB rigid for the RB2 and RB3 elements. So these are there in the while doing the modeling. So this is something what we need to convert this solid model into the FEM model. So this is something which is a like first step for the doing the simulation, and after that we are able to do the some solution on that. So suppose you have one bucket, okay, so this is like bucket, and you need to do some simulation on this. So directly not able to do the simulation on this. First you need to convert this bucket into the FE model. So this is how they have made it. In that the main portion has been converted into 2D, as you can see here. The sheet metal has been converted into 2D, and this is like mid surface, extracting mid surface, and on that mid surface we have applied the thickness. So it will directly take this volume. So similar way they have converted this bucket into 2D and this rod into 1D format, and they have given the connection with respect to the RB2 element which is shown here. So this is the first and essential step to do any simulation. We have to convert the we have to convert this 3D model into FEM model, and with that we have to pass all the criteria. So we have our element criteria, so it should pass through all the criteria, then only we are able to solve. This is something like you can make it you can make this tab into 2D, 1D or 3D as well. You can make this bucket into 3D as well. But why it is need to be done into 1D or 2D or 3D, that has been explained over here. So suppose this is a cantilever beam with some dimension like say suppose 25 by 25 and having 500 mm plan. So that has been, if it is 1D, that is like only 2 nodes, like 1 and 2, and they have given the 1 elements over here, and with that 1 element they have given the dimension to this. This is something like applying the property, and while applying the property you can give the shape of this beam as well as material and all to this beam. So while doing that they have given the shape as well as material to this beam, and they found that there are only number of degrees of freedom are 12 because they are containing only 2 nodes. So 6 into 2, 12 nodes. They had to write the solution, and they have found out like 105 Newton per mm stresses and displacement as a 4.23 mm. So they have just converted this into the 2D, as I mentioned, taking the mid surface of this, doing the meshing on the same, So if you are call my old friend.
किसने स्पीकर ने हाँ वो खुद से ही ले रहे हाँ श्रेयांश ओम प्रसाद क्या बना रहा था
It is not working. Suppose you have the beam. So while modeling into FE modeling, you just need to take 1 point over here, 1 point over here, and draw one line. This is like so with 2 nodes you can make this one beam. So if you want more accuracy, you can take more nodes over here. More nodes. So you'll get the more accuracy. So number of nodes will increase the accuracy, but how much node you can add on? Like you can split this into 100 nodes, 1000 nodes, or 1 lakh nodes as well. So it's depend on like if you are doing it for the suppose if you are with 5 nodes, you are getting solution within 1 hour, and if you are applying like 1 lakh of nodes, and if you are getting the solution after like 2 months, then we will prefer with the 1 hour solution. Because in the industry with the 90% of accuracy, the solution, the faster solution will be applicable or acceptable as well. And after some time, if you're like applying 100 nodes over here and 200 nodes, 300 nodes, 400 nodes, if you're splitting it, like applying the node is like splitting these elements. So if you're splitting these elements in small format, after some time, if you are doing splitting into 100 parts, or if you are splitting into 1000 part as well, by splitting into 100 parts you will get one accuracy result, and with 1000 nodes as well you will get one accuracy result, and those will get matched. So after some time the result will match, so there is no need to split it into further. So as someone has asked, if you're doing the NASA is using very small element size. They are using 0.2 mm, 0.1 mm element size. While I had read some defense things, they are not using that much element size. They are using 10 mm element size, as well as 20 mm element size for the foams, and which are not essential part in their perspective. So for that they are using bigger element size as well. But if it's come for the NASA and if it's come for the gun and gun holder, they are using the very small element size. So it's depend on the requirement of the accuracy, the element size got splitted. So earlier, in early stage, we are able to solve only for the 1600 node elements degrees of freedom, which is like I think only for the 400 nodes we are able to solve. So in the Germany they have built one system. So they have one specific station for that as well. That much the bigger system it was, and the first solution done was over there for the FEA, and after that the innovation get, and now we are able to solve for 4 lakh crore elements. So Altair has in one of the Altair press conference they have told like they are able to solve it for 4 lakh crore node elements count. They are able to solve the model. So this is something which is like now innovation getting, and they are having the bigger machines. Like we are using with 256 GB RAM as well as 32 processors, but they might have using the like in TBs. So for this much, like if you want to solve it with the 1 lakh nodes, or if you want to solve it with the 1 million nodes, then you should have the bigger specific machines as well. Because each node will do the node will have the so each node will have 6 degrees of freedom, and those 6 degrees of freedom will be converted into number of equations. So here will be 12 number of equations. So here will be the, if you're doing for the 2D, so like
स्कूल से मेरे को पापा बोले थे, पापा के स्कूल में था कि 8th standard से
so suppose this is your sheet which is like top view of that. Now you need to split this. So if you need to split this,
जब ओरिएंटेशन कुछ होता है तो लंच उधर होता था, देन फिर सब तोड़ने लगे, कारपेंटर शॉप सब इधर आ गए,
splitting.
हमने भी देखा है ना, हम जब कॉलेज में
splitted this.
मैंने 8 से देखा.
These are the nodes now.
7+
This look bigger, but and with this node you are going to make one element. So what will be required for to make any node? To make any node, the coordinates will be required. So if I ask him where are you, so he can say 0 0 0. So x direction, y direction, z direction, he will be in 0. If I ask him where are you, he can say 1 0 0. So that's like the coordinate of this. And if you want to make element, then the 4 nodes will require. So this node will have some specific number. This one as well. So if I want to make element, so I can say element 1. So in that I can get 1 2 3 4 node. If I get 3 nodes, that will be the tri element. If I get the 8 nodes, then that will be the hexa element. So the node will be defined with the help of coordinates, and the element will be defined with the help of node numbers. So how many nodes are there? That indicates it is 2D or 3D or 1D as well. So this is something which is like element and node. I'm doing 1D and through 2D. Okay, into this. So they have defined this with the help of the mid surface, and they had done the 2D simulation on this, and they get around 5454 degrees of freedom, and they, with that also they are getting 103 MPa stresses and 4.21 displacement, and they have converted this into 3D as well. So over there, as you can see, they have getting the more number of degrees of freedom, as they have considered the whole volume for the meshing. So they are getting the same amount of displacement and some near about the same amount of stresses as well. But as you can see, the element size has gone increased from here to here. So most probably, like most preferable one is a 2D one, which will give the more accurate result and reliable displacement as well. So we will always prefer 2D for the sheet metal, and for the beams and 3D model, it depends on the component how the behavior is, because you are not able to convert this into the sheet metal because it is having very variable thicknesses and all. So for all the castings and foam, we need to do it with the 3D. For all the sheet metal, we need to do it with the 2D. We can do it with the 3D over here, but it will take lots of time to converge and to solve as well. So if it is not essential or not required to do it with the 3D, we are avoiding it to make it into 3D. That's why we are doing 2D, and we are like expecting to less time. So this is like splitting the geometry with respect to the dimensions. If it is 1D, 2D, and 3D, and splitting them into the respect to element as well. 1D, 2D, 3D. So all the solvers will work with this beam, chord, tri elements, but depend on the solver to solver. If you are working in the Nastan solver, if you are working with the Abacus solver, if you are working with the OptiStruct solver, they have their codes. So if you are working with the Abacus, it will be like B31, B32. And if you are working with the Nastan, they will have like a beam, C bush. So depend on the solver to solver, the element type, defining the element type will also change. So this is like in general, but depend on the solver to solver, the element type, defining the element type will change. So any questions till now while doing the FEM modeling, or how we are doing the FEM modeling?
Hello, sir.
Yes.
Sir, questions will be asked in the end, so you can continue with the presentation.
So as Santosh has mentioned about this methodology, like how we are going to solve any problem. The old one was the experience method, there where all the time consuming things will happen, and the new method which is there, which is like a numerical method now we are dealing with, which is like the FEA and CFD are dealing with. And another reason one is the analytical method where the head calculations are going to be done. This is like 100% accurate method, but all the dynamics project problems are not going to be solved with this kind of approaches. But when you are shift to the numerical method, there is like a for the assumption. So you should require all the friction values and all. You need to take it from the assumption only, and that's why it is not more realistic but you will get 90% of accuracy result, and then you can go it for the experimental. If you want 100% accuracy result from the numerical method only, then you need to put all the input as very accurately, so that if you're using friction values, then it should be accurate. So if you're using any Young's modulus, Poisson's ratio, density, those should be point to point. So what NASA and other things are doing, they're having their tested data. Everything is tested over there. And from that, they are putting the values. But lots of OEMs and other companies are doing what they have some database from the previous, or they are taking the database from the other OEMs and they are giving it to us, and they told us like do this simulation. So this is not this is how we are not meeting the accuracy level. So one thing is like it's like a garbage in and garbage out. If you are giving the wrong input to the simulation, so it will not give the accurate result. And if your customer is asking like why we are getting the failure, you can tell them this is the input which we get, and this is output on that input. So you need to check the input is correct or not. So this is the first thing you need to check while doing any simulation, that the input which you get which are accurate or not. So if you're saying like density, so if you get the density for the steel like 2.7, so whether it is correct, so it is a density for the aluminum. If you're getting the density for the density is at 7.9, okay, that's a steel density. So you need to question yourself before doing the simulation as well, because you need to put all the values by yourself in the while doing the simulation, all the material values, all the thickness values, all the temperature values by yourself only. So machine is just going to solve the simulation, but the input which is going to be there, it's going to be there from your side or the customer side only. So you should be careful while doing this, while putting this value or while giving the input, or you need to double check the values with the customer as well. So you need, okay, say suppose this is cantilever beam and I'm doing the simulation for this. So I have as I mentioned, I did the beam thing. So I have split it into 100 nodes, and I did the beam with the help of element C-beam. I have given the property, so it will be in the shape like this only. And I have applied the material of steel over here. But while applying the material, I have changed the density. So it has given 7.9 into 10 raised to -9 ton per mm cube. But I have given as a 2.7, which is like aluminum density, and you are getting some wrong result. So who will be responsible for that? So the responsibility is like the input which you are given. So you are going to be responsible for any failure. So all the input which you are going to provide or which you're going to put should be accurate only at the first time only. This is something about the input, and now we will check about the analysis. There are like various type of analysis depend. So first thing is like who defines the analysis. So I need to do the linear and non-linear analysis for my particular product. So for the exhaust system, I want to do the linear and non-linear analysis. But who defines this? This has been defined by the SOR, because our SOR says like your component level durability should be for the 2 years. So it should be survive for the 2 years or 10 million cycles. So if it should survive for 10 million cycles, what they need to be done? So what our global team has been done, they have tested it for 2 years with like number of loads and number of boundary conditions, and with that they have some derived some analysis. So each and every OEM and all the product-based companies are doing in such a way. So they have tested their data with various loads and various boundary condition. Boundary condition in the sense of boundary conditions defines the your rigidity of your components, or how you are going to mount your component on other components. So that has been defined by various way, and while doing that, they have did some certain criteria for each and every analysis. So in the linear analysis, there are like two analysis. First is a static analysis and second one is a dynamic analysis. So static is like not, it's not having the moving condition, right? Only in the dynamic it is a moving. So static will be like self weight or the gravity load. So say suppose you're sitting on the chair, and your CG will be over here. But all the, as I mentioned, like no need to define this human being. So you need to evaluate this, how many, like how much durability of this chair, or how many years it will survive if like 70 kg person is going to fit in on this. So you need to check like the CG of the person, and you need to check where it is going to be rested. So like I believe the 80% of weight is going to distribute it over here, and 10% of the weight is going, 10 or 20% is going to distribute it over here. So you need to make such kind of two boundary conditions with like given CG. One is over here, and you can place this over here. So if you can, it will look like this. So 2 CG, which is having the nodes, and the distribution of with the help of RB2 and RB3 elements. So you can give mass directly over here. So if it is containing 70 kg, so you can give it over 55 kg over here and 15 kg over here, and you can do the simulation for this chair. So if you want to do it for only for the chair, then no need to do it for with this CG and this mass. You have to do it with this only, this mass. Now the question will come, like if you applied this 65 or 55 kg load on this, so if you are getting the stresses in like plastic, this elastic limit only, so if it is coming in this region only, so it is not going to fail, right? So it will not be in the failure limit. But there is something like fatigue. So due to the repetitive load, what is going to be failure, that need to be derived over here. So we need to do the fatigue now. So if it is in the your region where K, your stress is directly proportional to strain, if it is obeys the Hooke's law, then you need to go it for the fatigue analysis at that time. So this is something. So the thing is, like, it's not essential to convert each and every body to the FEA. Sometimes the like weightage of this component on other component should be considered only. If you want to model this, it will take hell lot of time. So, and which is not preferable in the FEA. This is one thing into FEA. So static analysis, when we are going to do static analysis, so like in the very like steady state only, we are going to do static analysis. Say we need to evaluate for the chair, then only we are not going to do the static analysis. So, as Santosh has mentioned, there are two systems. There is one like cold end, and others are the hot end. So cold end are which are going to mount it on the chassis, and hot end are there, those are going to mount it on the engine side. So all the engine side components are going to mount it with the help of the brackets only. But all the chassis mounted components are mounted through the rubber bush. So those are like hard rubber. So those hard rubber will have some stiffness, and those are going to displace with the self weight. So for that, we are going to do this static analysis. And now the static analysis is like with the help of G values only, gravitational value. Now the second topic in the linear analysis is a dynamic analysis. So in that we are doing the model analysis, FRF analysis, and PSD analysis. So anyone can tell me the definition of the model analysis? The definition of the model analysis and the formula as well. Any one of you? Hello, can you hear me? Yes. So definition of the model analysis or definition of the natural frequency, you can say. Natural frequency.
Sir, analysis, we study the properties in the frequency domain.
Yeah. So definition of the natural frequency. Or frequency. Definition of the frequency.
The natural frequency is basically the frequency at which the system tends to oscillate. For example, in a vibration.
Yeah. So body tends to oscillate, right?
Yes, sir.
Body tends to oscillate without any external force. So those are like natural frequencies are like the body where the external force has not been given. So in that, the body tends to oscillate without any external force. So those are the mode shapes. Like if you are driving in a car, so at particular RPM or particular speed, you are getting some vibration at your car. So suppose you are like going with the 45 km per hour, you are getting some vibration. If you are going with the like 55 km per hour, you are getting some vibration. Those are like natural frequencies of your components or your vehicle components. So this is what we need to check. And if we are deriving, we are doing it for the exhaust system, we need to like calculate the natural frequencies or natural frequencies of our component, and we need to check with the engine natural frequencies. So if engine is having 10 hertz, 24 hertz, 50 hertz as their natural frequencies, and if you are getting like 10 hertz and as our exhaust system frequency as well, then the then the same frequencies of engine and the exhaust system, then this tends to go for the vibration into the your like in your car. So those should be avoided. So all the OEMs will provide their engine frequencies to all the tier 1 and tier 2 suppliers, and they says like these are the natural frequencies of our engine, and those should not be matched with your component. Okay. So what is the like basic formula for the natural frequencies, like root k by
root k by n.
Yeah, yes, exactly. So if I getting some 10 hertz frequency of the engine, and if exhaust system is having the 10 hertz, so if you want to increase the frequency of exhaust system, what I need to do? With this formula,
either increase the stiffness or lower down the mass.
Yes, either I need to increase the stiffness or lower down the mass. So I have one more presentation for you. So this is like this is something confidential, that's why I'm not able to show the whole component. But with this 5mm bracket, this is like one cone connected to this, and I'm getting one like this is like 105 hertz as a first natural frequency of this. So if you want to increase the this frequency, as you told me, like increase the mass, right?
No, sir, decrease the mass. Increase the frequency.
So decrease the mass, you will get the higher frequencies, right?
Yes, sir.
Okay, so if I increase the mass, what I will get?
Lower frequency.
Lower frequencies, right? So now I did something with the 10mm bracket. So over here I have increased the mass, right? I have increased the mass, right? With the 10mm bracket I did it, and with the 5mm bracket I did it. Okay, with the 5 mm bracket, I'm getting 105 hertz, and with the 10 mm bracket, I'm getting 133 hertz. So I'm increasing the mass. Still, the frequency got increased. So anyone can tell about this? Why this frequency got increased? So I'll ask this question again. So as this formula says, the m is denominator, right? So it is inversely proportional to frequencies, right? So if you increase the mass, the frequency will lower down. If you decrease the mass, the frequency will rise up. Besides that, I did one simulation. So in that, I have one bracket is with the 5 mm, another bracket is with 10 mm. So I have increased the mass with this. Obviously, like if I did it with the 10 mm, this mass is going to be increased. Besides that, I got some higher frequencies. Anyone have idea about this?
What is stiffness? Stiffness changes or remains same?
Yeah, this is the one thing you need to consider now. The stiffness with the 10 mm bracket is going to be higher, right? The stiffness with the 10 mm bracket is going to be higher as it is with respect to 5 mm bracket. You can see the moment over here with the 5 mm bracket. And with 10 mm bracket, you can see it got more stiffer now. So it's not only the, if you are like decreasing the mass, that time only the frequency will goes up. You need to check the stiffnesses as well. So this will help when the like cone mass will get decreased or cone mass will get increased. So I have done this simulation as well with the same thicknesses, but I have increased the mass of the cone. Now the frequency got decreased. So where the mass is going to increase or decrease, that also like depend the frequencies, whether it is going to like change or not. So understood, like in the first case, we did it for the bracket. We have changed the bracket from 5 mm to 10 mm. With that, we got some higher frequencies. Why we got the higher frequencies? Because the stiffness of the bracket got increased, and this bracket is going to be fixed. Like this is the fixing point. These are only the fixing point. And this whole cone is in the free. So it's a free only, the cone. Now, what I did, I have increased the thickness of this cone. Besides that, I got some lower frequencies. Because as this formula says, if you are increasing the mass, the frequency will lower down. So this always over here when we applied the thickness of the cone, but not for the bracket. You need to check if the addition of the weight also increasing the stiffness, then you need to do it with the simulation. And this you are not able to predict. Like if you are having the 105 hertz with 5 mm bracket, with 10 mm how much you are getting, this is not you are going to predict. You will say directly that the frequency will rise up with your experience, but how much you are getting, that you are not able to predict. But in other way, in static analysis, which is stress is directly proportional to strain, right? Your force is directly proportional to your stress. So in that, if you are getting 1 Newton, if you are applying 1 Newton and if you are getting 10 MPa, then if you are applying the 10 Newton, then you should get 100 MPa as a stress. Because in the static, it is like directly proportional. But in the dynamic behavior is something different. Over there, you will apply some damping and the stiffnesses as well. So like f of t is equal to m double dot x plus c of x plus k of t. So, k of x. This is like acceleration, velocity, and displacement will consider into dynamic analysis. But static is like directly proportional limitation. So over there, you will get, if you're increasing the force, the direction of that, the stresses will increase. But in the dynamic analysis, this is not like directly proportional. So you're not able to predict how much you are going to increase with, but you can predict like okay, this is adding some stiffness. The frequency should rise up. So do you know like how much you are getting the frequency for this bracket, or any component is having the frequency till what limit? Like it will be there for 1000 hertz, or it will be there for 10,000 hertz. Are you aware about that? So are you aware about your car will have like till what hertz the frequency limit is? So we'll think about the car only, not about the other things, not about the missile case and shelter and all. So can you think like till how many hertz you get the frequency of the car? So what will the range for your car, the frequency range? Are you aware about that? Any one of you? How to derive the frequency range for the car? For any object, you can say.
No.
Okay, so I will do it. So what is the engine capacity? How you will define the engine capacity? Like what is the maximum RPM of that engine, right? That will be your engine's capacity, right? The fly speed. Maximum RPM will define your engine capacity, right? So say suppose you are having the 3600 RPM as the engine capacity. So can you tell me the lowest engine low limit of the RPM? What need to be considered for the low limit of the RPM? So that will be the ideal RPM. The ideal RPM will be your lowest limit. So say suppose this is 600. So this is in the RPM format. Now we need to convert this into the RPS format. Revolution per second. So where is 3600 by 60. This is we are getting the RPS, and by 60. Then we are getting a 10 RPS. So if you are say suppose you are having the 4-cylinder engine, then it will be the into 4. It's like 20 to 240 hertz is your engine limit in the terms of the frequencies. I have multiplied this with the 2. I have multiplied this with the 4. Why have I multiplied with the 2? Because if you consider 4-cylinder engine, the 2 cylinders in the power generation and 2 cylinders in the power transmit. So 2 engine will be in the sewer. So that severity limit we have considered with this. So 20 to 240 hertz is your frequency limit. So what we'll do, while doing the model analysis, we will give some input such as we'll give the EIGRL card. In that we will mention please tell us the mode in between 20 to 240 hertz, and that can be derived directly from the software, and we will check those modes with the engine modes. If those are not matching, we'll say like, okay, these are the natural frequencies which we are getting now. Now we need to evaluate that. So some natural frequencies are there, as I mentioned, some 45 hertz, 45 kilometer per hour you are driving with, or 55 kilometer per hour if you are driving with, you will get some vibration in your vehicles. So those are the natural frequencies of your vehicle. So what we'll do, we'll apply some external load on that natural frequencies, and we will evaluate for the dynamic analysis. So for that we do FRF analysis and PSD analysis. And while doing that, we evaluated with the temperature, because if you are doing it with the normal temperature, your Young's modulus will be 210. If you are doing with the 800 degrees Celsius, your Young's modulus will low down till 70, 80 or 110 MPa. So this is what we have, something which is tested data, and we need to evaluate this for the actual condition. So that's why we are doing it with the temperature, evaluated temperature analysis. So this is something which we are taking from the CFD. So CFD team is doing it for us. So they are implementing all the worst case conditions on the CFD model, and they are finding out the what are the temperature on each and every cone and each and every bracket, and they are providing it to us, and we are implementing those temperature on each and every node, and then we are simulating this analysis like FRF analysis. So then we are getting some values, and say suppose your cone is at 500 degrees Celsius, and if you need to evaluate, say suppose you are having the 20 at 20 degrees, so you can say the yield limit is 210. But if you are having it for the 700 or 500 MPa, then we use this tested data to for the factor of safety as well. So this is something we do into FRF analysis. So this is something which is dynamic analysis. First we find out the model analysis, and then we do some FRF analysis by applying the engine load on that. So if you consider the, if you like want to do it for the defense, if you want to do it for other customers, then we do same. But in the defense and any other systems, they are steady, like they are not having something which is engine is generating some power. So for that, we are doing the mass participation factor. So when we get like if you're getting some 10 nodes, which say suppose 25 and 27, so we'll do till 36 first 10 node, and we'll take how many mass participation factor is there in XYZ direction. If it is more than 90%, then we'll say okay, this is like okay for us. So 90% is a criteria. So till that point we check the frequencies for other heavy metal or heavy engineerings. So it's like their specific criteria. All the heavy engineers have their specific criteria, 90-95%. So till that point we check the natural frequencies and we evaluate those natural frequencies with this dynamic analysis, which is like FRF or PSD analysis. FRF is like a frequency response function analysis, which we do over here. So next one is a non-linear analysis in the FEA. The first one is a linear, the second one is a non-linear. So why it is required to do the non-linear analysis? Non-linear analysis is like when the geometrical changes or contact changes or material changes are there, at that time we need to do the non-linear analysis. Or in other way, if it is like in the elastic limit, you can do the linear analysis. But if it is going into the plastic limit, then we have to perform the non-linear analysis for the same. So this is something which is we need to do the non-linear analysis. So we do the non-linear analysis as a thermomechanical fatigue analysis in our in the Teneco. So in that, like in the engine is like heating cooling is going on. So what we do, we run the engine at maximum RPM and with full load, and we will check how much time it required to make it constant or to make it like a higher temperature only. We take those time and we check, like we do it for the ideal RPM now. We run the engine for the ideal RPM, and we check the timing for to reach the temperature to the ideal RPM. So when we get some constant temperature, we take those time as a cooling time. When we get higher like heated up temperature as a constant temperature, we take it that is heated up time. And with this heating cooling cycle, we do this thermomechanical fatigue. So with this heating cooling cycle, what is going to be done on the component level, that is going to be evaluated from here. So this is something is from the heating cooling. So in the non-linear analysis, we are using the SN curve, but in the linear analysis, we are using the stress strain curve for the passing criteria. So this is where here all the things are depend on the yield limit, where it is like you are getting the infinite life or you are getting the finite life. So this is how we are evaluating the non-linear. So this is like specific for the Teneco, But other things like other OEMs or other heavy engineering, they do such kind of things as well. In that, the model and the FRF and static analysis are common for all the evaluations. But these non-linear things will change depend on the applications to applications. So last thing we do is a report. I think I need to stop. Okay, I'll just fast forward. The last thing which we do is a report. So in that report, the boundary condition will be like essential to make, as I shown it here. So this is something I have fixed. So I need to put this picture, like I have fixed this point. I can take this bracket as well, and I can fix this point, but you will get some higher frequencies. Those will not be realistic. So those, if you want to make some realistic result, the boundary condition will be proper only. So you need not to fix this bracket. You should fix this bracket as you are finding out the analysis for this. There will be some casting bracket after that, which will be more rigid, and we will not have the frequencies on that. So we are neglecting that. As well as sometimes it's like customer confidential thing. That's why those cylinders are not going to be provided from the customer. So at that time we need to take this bracket. But you always take environmental components to fix your component. So this is something which is essential, is like boundary conditions, the material which you have applied, the thickness which you have given. So everything's depend on that. So it's like garbage in what you are doing on that. So that should be documented. So it's like your project, it's like in January and some modification has been happened in the March, and the CAD engineer has not provided you that drawing or that CAD model, and you did it with the like January model. So he can say, like customer can say, my photo got failure, and FA is responsible that for that. They have given the green, like go ahead in their report. So this should be documented. So the material thickness for the FA model is something which is important. After that, we do the stress values and factor of safety for the static and dynamic analysis. And for the non-linear analysis, we do with the number of cycles. And if it is getting failure somewhere, you can suggest the design modification as well. So I think we have some. It's 1 p.m. now, and I have limit till 1 p.m. only. So this is something we are doing. So this is something like when the FEA is divided into FA modeling, solving the problem, and reporting. So any question and anything you need to ask. Santosh, you need to add on something? So anything you need to ask, like in the how the model frequency.
Yes, sir. So now we are open for question answers. If you have any questions, please raise your hand.
Yeah, if someone want to ask about CFD also, because that I got dropped from the discussion in between, so they can also ask.
Yes, Panis.
Yes. I think that's it.
If geometry is a bit different from the drawing, how will it influence the result? And is it good to be aware of that? Like if accuracy is what we need, like what we expect to be the solution.
Yes. So if it is you will get the 2D drawing as well as a CAD as a reference. So if it is differ, then you should send back to the CAD engineer that it is differ from the 2D drawings and which needs to be considered. So there might be the updated 2D drawings, or there might be the updated CAD. So if those are not matching, then you should send it back to the your like internal customer or to the customer. So I think this is what we do as well. So if you are getting some bracket with 4 mm and in the BOM or in the drawing it is says like 2 mm thickness, so we are not going to simulate for the same. We directly send it back direct to the customer or to the internal internal customer and saying like this is not matching. Please like send us the updated CAD or corrected drawings. Then only proceed for the same. Because we believe doing something right at the first time, because it takes a lot of effort and time to simulate this, and if some design changes are going on, we are not going to we are not doing the simulation for the same. Yes, I think
Now, Yash Chaudhary.
So it's depend on what you need to perform. So if you need to perform the nonlinear simulation, then the abacus and Cs are preferable. If you want to perform the linear analysis, then they will perform the MSc Nastan, NX Nastan, OptiStruct. If you need to perform the crash, then they perform the radius. But for the pre-processing, most of the companies are using the hypermesh. Like I think 90% of the companies are preferring the hypermesh. That is like Altair software, and most like only 10% are preferring for the ANSA. But it's depend on the say suppose in the from the last 50 years, the Mahindra is using some software, and all over the global they are using the same software. Then it's like depend on the what they are started with as well. So in our team, the German team has used MSc Nastan, and from last 3 or 4 decades they are using the same software. So all over the global we are using the MSc Nastan as well. But I think for the nonlinear, the abacus and ANSYS are preferable, ANSYS workbench. And for the linear, most of the companies are using the NX Nastan as well as MSc Nastan and as well as OptiStruct. And for the crash, you can see lots of opening on the LS Dyna and as well as the radius. We can do it into NX Nastan or Star CCM from the Siemens. Santosh, you need to add something?
Yes, it's CFD. So I would say that ANSYS Fluent and Star CCM is used more into industrial domain. So you can choose out of both of them. But if you want ease of simulation setup and ease of meshing, then I would suggest if you can use Star CCM, that would be better. What kind of problem you have mentioned? It's a wind turbine, right? I think you can use Star CCM.
Hello, Santosh sir. I asked you that question and then you got disconnected about hydrodynamics and aerodynamics, the parameters we should have. So can you
Okay.
please explain that again?
So I was saying at that time that in industrial practice, the theory is not, you can say, it's there in the use, it's there in the use, but at the back end of the simulation. And on the front end, you might need not to be go every time that deep, but as you are comparing hydrodynamic situation or hydrodynamic case with the aerodynamic case, I think they both differ into what kind of situation they are facing. So I think they totally go into different direction. So even your this numbers could appear into the picture to segregate what kind of methods or models will be used. But I think it's the basics or the objective of the simulation, where actually in both I think it's more towards the resistance of the flow to the structure, like either it is some kind of boat, submarine, whatever, or on the other way it's the resistance to the aeroplane or flight, whatever. So in that sense it is somewhat similar, but on the other sense, because one is compressible fluid, air is a compressible fluid, so its properties will be totally different, whereas here there will be resistance from air as well as from the fluid or the liquid, the water. So there will be definitely some complexity level higher in the hydrodynamic flow simulation, and I think in exact form which models will be used is difficult to say. I think in both places you might be using this K epsilon, but you might use some different form of it in both the cases. But definitely K epsilon can be used for both the cases. But in depth, you might find, because simulation, even Omkar can back up me on that, in the simulation software, if you go inside, there are too many parameters available to change, and that change in the parameters can alter your result. So generally industrial practice stands like your this small parameters other than the basic boundary conditions should not be changed. So it should be standardized so that you can compare your result development over your multiple trials. So for that matter, generally most of the industries standardize their parameters as per their simulation domain. So in that sense, there will be a difference in the aerodynamic versus hydrodynamic. It's not purely hydrodynamic; it's hydrodynamic plus aerodynamic in the both kind of situation. So there will be definitely some additional parts, and even you can say there will be like two domains involved at a time, or um, two fluids involved at a time. So
Okay, sir.
it will be quite
Got.
different.
Yes, sir. Thank you, sir. Got.
So actually, I have a doubt, like how to interpret FEA results. Like even if we already have the proper values from our FEA analysis, still we need to decide to interpret the final FEA results. So it's very confusing for us right now. So could you suggest any parameters which we need to focus on?
Santosh, or I will give it. So
Omkar, I think it's for structural.
yeah, so I will get this. So I think so. We need to check first of all, like if you are doing the, as I mentioned, like we are doing the FRF analysis, right? So in the RFQ stage, we are applying some 0.1 mx and 0.2 mm excitation on the from the engine. But when we take some excitation from the engine, like those are the tested data, something which we are doing the measurement. So those tested data are converted into the hour format. So it's like they are having some strain gauges over there. So from that they are taking some vibration, and those vibration are converted into hour data, that is like in the acceleration, and those data we are giving it into the hour model, that is like we are providing it basically on the brackets and all where it is going to be mounted. So those are very essential or very like very much impacting data besides the material. And those data, if you are implementing it accurately, you will get the same failure. So I will tell you one thing, like when the BS6 launched and when the Mahindra was developing it for they are doing it for the first project, BS6 first project, D72 they are doing it. And then at that time what happened, they are getting some field failure on the beauty sheets. So they were having some beauty sheets which are like on the exhaust system, and on that we have not, none of them are like did the simulation for the same, because it's like a beauty shield only. So everyone neglected while doing the simulation. We neglected, the OM also neglected it. But when the actual run happened, when the actual testing happened, we got some failure on the beauty sheets. So how we need to overcome on that? So we did the some measurement on that. So while running on the tracks, so there are like lots of tracks are there which will define the worst case. Like from that we have checked on which track we got like higher vibrations, higher accelerations. We taken those vibrations and converted into the acceleration. Those response has been converted into acceleration, and those acceleration has been given into our model, and we got the same failure where they are getting. So as I mentioned, like input is which is very much essential. If you have the correct material data, so material data which we are using into the while providing the product, that has been tested in our test labs. So we have did this cup cone and all the things, and we have our own stress strain curves. And if you have that, then the inputs is essential. So first and most thing is like you should have the material, the tested material, which is like which you have provided to the OEM. And second thing, you should require the exact data or exact test measurement data from the all the OEMs, or exact excitation which is coming on to your system from the engine or from the road load.
Okay, sir. So thank you so much, sir, for this comprehensive presentation. We really gained a deeper knowledge about the concept of FEA, and I'm sure it would be helpful for all of us in our academics as well as in our project.
Thank you, Aditi. Hereby we conclude our presentations. I request all the attendees to turn their cameras for a moment. Thank you. Now, I call upon the Secretary of MESA, Malcolm Dias, to give a vote of thanks.
Thank you, Pratham. A very good afternoon to one and all present here. As the Secretary of MESA, it's my honor and privilege to extend a vote of thanks on behalf of FCRIT Vashi and MESA to all those who have contributed in a way or the other to make this event a remarkable one. I would like to take this opportunity to thank all our dignitaries for sparing their valuable time and enhancing this event by their presence, and also for endowing their technical knowledge and experience with our students. Let me express my gratitude and appreciation to our Managing Director, Reverend Father Almeida, our principal, Dr. S.M. Cole, and our HOD, Dr. Nilaj Deshmukh, for their continued support. I would also like to express my heartfelt gratitude towards the management of Tenneco Clean Air India Private Limited. I would also like to acknowledge my MESA team for their priceless contribution and praiseworthy dedication in making this event possible even during the pandemic situation. Also, I thank all the teaching and non-teaching staff for their immense support. Before I conclude, a big thank you to all my fellow mates for their active participation throughout the event and for sending in their innovative articles for our Urja magazine. Also, hearty congratulations to all our achievers. Thank you.
Thank you, Mr. Santosh, Mr. Omkar. And our student will definitely will interact in future also regarding the different project activities.
Yes, definitely.
So, Nilaj sir, with this, I would like to thank everyone for being a great audience. Here, we conclude our session, and attendance as well as feedback forms have been circulated. Please make sure you fill them before leaving. Thank you, and have a nice, great day ahead.
Thank you.
Yeah, thank you all.
Thank you, sir.
Thank you, sir.
Can you disconnect?